总监 Magnus Maria Heller，恩智浦的产品营销经理 Mike Van Harder，以及红科智能互联技术主管陈浩6位嘉宾，为大家介绍 CAN XL 的功能优势与传统协议网络的对比，以及目前的市场情况。再次感谢各位观众朋友的到场以及行业嘉宾们的支持。我们今天的研讨会即将开始。那么首先呢，我们先请红科的 CEO 陈秋苑陈总为我们来一个开场的致辞，欢迎陈总。
好的，非常感谢应奇的主持和介绍。也非常感谢我们所有在线的用户朋友们。那很高兴借此机会呢，我能够代表红科的所有同事们，在这里跟大家这个简单的欢迎词。首先呢，我想用3个关键词来开始我的这个致辞。这3个关键词分别是感谢、感激和感恩。其实红科从2009年底开始，我们就进入了 CAN 总线的这个业务领域，到后来2012年的 CAN FD 以及2019年我们红科开始去介入 CAN XL 的一些标准的制定和一些市场的反馈等等，开始做一些工作。那么其实我们在整个的过去的15年期间，红科都有不断的参与以及不同的产品线以及不同的业务在推出，在帮助我们广大的大中华地区的用户们再去为我们的 CAN 总线的开发，为 CAN 总线的应用去赋能会去提供我们的一些支持。所以非常正式的借这个机会，感谢所有的 CAN 总线技术领域的同事们、工程师们，然后以及我们的所有的专家朋友们对红科团队的支持和信任。我们的业务其实也从最早期的，在这15年期间，我们从最早期的 CAN 代码、CAN 的协议站、板卡分析软件不断的发展，截止到今天，我们红科推出了非常多红科自己的一些产品和方案，比如 CAN 总线的一致性测试系统，这个已经很多年，我们的一些Hardware and Loop 的 Hill 的系统、采集系统、软件服务包以及不同的软件之间打通的一些工作，以及我们的培训和测试的业务相信大家也知道，红科在2012年开始就推出了很多 CAN 总线的一些培训业务，再到2020年我们在全网推出线上的直播课程，那么到今天为止，我们 CAN 总线相关的主题课程已经超过100节那这一路走过来，有不离不弃，不断的出谋划策，指出问题，提供非常多中肯落地、合理化、很有建设性意见的用户朋友们，也有我们过去失败不断总结，然后再成功，然后再去迭代的很多的一些宝贵的经验，才成就了今天红科在 CAN 总线领域的一席之地。所以用3个感恩、感谢、感激、感恩来感谢我们所有的朋友们。那最后呢，我也再讲一句，就是想用一个关键词来简单的做个总结，那么就是共创。为什么会说共创呢？其实红科一直不认为自己只是一个简单的乙方。那么从2022年开始，我们跟某个主机厂开始一起共同研发了一款系统那么可能到明年我们就可以开始正式的面向市场销售那之前我们是定制的一款产品，那么这个呢，在这里面我们有非常多的收获和体会，然后我们也意识到了自己确实成为这个深度参与的一份子，我们应该有一些回报。我在今年的5月中旬，我在德国的巴登参加了ICC 的CAN Conference， 这是在上一次已经14年前了因为疫情推迟。那么我的很深的感受就是，整个大中华地区的的参与者只有我1位然后另外还有2位来自韩国的就整个亚太区的面孔只有3位。 那我当时很深的感受，就这2天的闭门会议，非常多的真知灼见，非常多我觉得对于我们的用户有非常多，不管是我们是供应商，还是主机厂，还是应用者，还是开发者还是系统集成商，非常多的很好的一些启发和 idea。所以当时2天会议的时候，我就马上跟其中我认为非常高价值的几位嘉宾，就今天在屏幕上大家可以看到的是几位重量级的大咖我们都是 XL 的创始成员然后跟他们讨论，邀请他们来举办一场针对中国的，只是针对大中华地区的我们的这个XL 的这种会议，我们一起共创，我们一起去共生，我们一起去共同成长，一起去分享全球的技术成果所以我想用这个小故事来去举例说，我们希望有很多不同层面的一些共创跟大家一起去共同的，我们最重要的是一个结果，不管这个结果来自哪里，途径是什么，那我们希望在最短的时间之内，我们能够借助各种途径，帮我们各方拿到更好的成果。好，所以最后有请把时间交回给应琪，感谢我们今天下午所有的大家的时间。好，
好的。
Hello，应琪。
好的，稍等一下，感谢陈总这边的演讲，那么大家都知道稍等一下。那么大家都知道 ，CanXL 技术工作呢是在 CiA 协会中完成的。作为创始人和技术先驱，我们也是非常荣幸的邀请到了 CiA 的2位 CanXL 技术专家，协会创始人 Hoja Zetwangje 以及 CEO Rainer Sisman， 他们会重点介绍新一代CanXL 的主要功能。那么在本次研讨会期间呢，在评论区互动的观众都可以参与线上抽奖，欢迎大家多多留言，有机会领取现金红包。相关的中文 PPT 我们也已经分享到了社群内，大家可以在评论区扫码进群，对照中文课件可以更好的理解咱们的演讲内容。第一场演讲即将开始，接下来就让我们随 CanXL 创始人与 CEO 一起了解3代 CAN， 从 CAN Classic 到 CAN FD 再到 CanXL 的整个内容。So Mr. Zetwangje and Mr. Sisman, please begin your speech.
Oh, sorry, Inchi. So all the speakers, maybe we can say hello now to all the audience, and then maybe we need to turn off the webcam. Okay, so 不好意思，我邀请所有的演讲嘉宾一起跟大家 say 个 hello， 然后我们待会每一个主题的时候，我们再打开 webcam 来给大家见面。好 ，Okay, so Holger, this is your turn.
Okay.
Thank you.
Okay, so welcome from the CIA side. Rainer Sisman and myself, we will present the first speech, and it's titled From CAN CC, which means Classic, via CAN FD to CAN XL. But before we start with the technical topics and issues, then we will introduce ourselves. So my name is Holger Zeltwanger. I'm an electronic engineer, and I was also a technical journalist for more than 40 years, and initiated the foundation of the non-profit CiA Association. Since 1992, I'm in the board of directors, and in addition, I have different roles in standardization bodies, in international ones like ISO, like IEC, SIE, and also in national ones like DIN in Germany. I hand over to Rainer. He will have the first part of the presentation, and then I will later on join you again and provide additional information.
So, thank you, Holger, and thank you for the brief introduction and the honor of being part of your webinar here. And my name is Rainer Sisman. I hold a degree in electrical engineering too. I've joined CAN Automation in 2004. In the meantime, I am the general manager of the CAN Automation GmbH. It's the commercial arm of the association with the main objective to organize the association, to provide all the services that are intended to be provided to the members of CAN Automation, and to provide them in the intended and best way. In addition to that, I'm a speaker on several conferences. We present CAN Automation on fairs and in international standardization. So not that many standardization groups as Holger does, but for example, I've standardized the communication, the CAN-based communication in light electric vehicles. public charging, or in the rail vehicles, can open on the consist level. And I'm a member in further European or German mirror groups. Yeah, in brief, to CAN automation, maybe you don't know what is CAN automation, who is CAN automation, why does an association like that exist? So CAN automation, or briefly CiA, is the international users and manufacturers group that develops and supports CAN Open and other CAN-based high layer protocols. The non-profit group was founded in 1992 to provide CAN-based technical product and marketing information. The association fosters the image of CAN technology and also provides a path to future network technologies. So what does this mean? We promote CAN, we present CAN as a good alternative for everywhere where something is to be automated as embedded network. And we try to assist people in overcoming their technical challenges if they are CAN related. And so we not just network devices, but we also network humans. So we have established since 1992 a huge social network of CAN experts. And therefore, we invite also our Chinese community of CAN users to join this social network and to rely on this to benefit from this social network. So if you have any CAN related challenges, then at least you can contact CAN automation and maybe we can help you directly, or we know someone who is very familiar with these subjects you are dealing with and can assist you so you can overcome your challenges much more easily. CAN automation is located in Germany, in Nuremberg. So if you know Germany, for example, from the Oktoberfest in Munich, so we are about 160 kilometers in the north of Munich. And here, for example, the SBS fair, the Embedded World Fair, some very interesting fairs for this subject to take place. So maybe you have the chance coming to Nuremberg, so you can also visit us at the CAN automation office to discuss CAN related questions. Otherwise, we are available via email or other social media channels, so you can contact us. CAN automation, what we are doing, we mainly maintain and develop CiA specifications with the aim to provide CAN-based devices, solutions, components, a certain degree of plug-and-play capability, of interoperability, and therefore we provide a neutral ground where companies can meet according to antitrust laws and can discuss how to overcome in a harmonized way certain CAN-related challenges. Furthermore, we provide some marketing then for these kind of specifications and these activities. So one of the famous one is the CAN newsletter magazine that appears quarterly, and it's also in China rather easily to receive as it's available as a PDF version. If you are looking for CAN-related products, tools, then maybe our product guide is a good source for information here. And if you want to know why it is reasonable to use a CAN-based solution in this or that application field, or what are benefits of this or that CAN generation, then we provide some brochures on our website where you can get the information. On the other hand, we have also some technical-oriented services, educational services like trainings also for engineers in China. We offer the possibility via web-based seminars or on-site seminars to train your staff. And furthermore, we offer testing services for CAN Open. We have conformance assessment. On the other hand, for certain application fields, we organize together with our members interoperability tests, or more easily to speak, simple plug fests, where you can double check whether your implementations are interoperable with implementations of competitors, of other actors active in the market. Yeah, so much in brief with regard to CAN and automation. Once again, warm welcome to this event from our side. So briefly to our topic. So from CAN Classic to via CAN FD to CAN XL. So in the late 70s, early 80s, the complexity in automotive in-vehicle networking increased that way that it was via direct wiring concepts very difficult to extend the existing automotive wiring harnesses via further functionality. The cabling had a lot of weight, And therefore, the car makers came to the conclusion that it's not very future-proof, the current way networking goes on in the cars. And therefore, they came to Bosch and said, could you assist us? Could you help us in developing something to simplify automotive in-vehicle networking? And the development was presented then in 1986. So you see here the first press release from these days. And there Bosch presented the controller area network, or briefly what you call now today CAN, or more specific today CAN Classic, or abbreviated with CAN CC. So from these days on, CAN Classic made its way into the cars, but it was not limited to the use in automotive applications. So very soon in the 90s, the CAN migrated to truck applications, heavy-duty vehicles. In the meantime, we find CAN in building automation, access door control, elevator control. We find CAN-based solutions in medical application fields like X-ray stands, communication to contrast media injectors, patient beds, and acute care units. Furthermore, we find the CAN in energy management applications, energy generation, so solar power plants, windmills. So in almost every area where something is to be automated, we find CAN-based networks in the embedded area. And we can say sometimes CAN is the dominating network, like in commercial vehicles, construction vehicles, heavy-duty vehicles, and sometimes CAN is just available in a niche market, but in general, we find it anywhere where something is to be automated. So from this side, the situation looks very promising with regard to CAN-based technology. Nevertheless, we see over the years more and more requirements have been placed on embedded networking. And therefore, we have also to think about how can we meet today's and also future's requirements to embedded networking, also in CAN-based communication. And the first step came then in 2012, when Bosch presented on occasion of a CAN Automation's International CAN Conference, the CAN with flexible data rate, so to say, the second generation of CAN, which provides a higher data throughput in CAN-based networks. And further requirements came up, and also those have to be met, maybe a little bit earlier than we would have expected that, but already end of 2018, beginning of 2019, the development of CAN XL, CAN with extended data field, started and was then finalized in 2021, and it's meanwhile internationally standardized. So you see on this slide the history of the documentation, respectively the specification and standard of standardization of CAN, which started with a presentation at the SAE conference in 1986. Then you have the Bosch specification available in 1991. It's rather famous, the CAN 2.0 AB, because it's also today still mentioned in some CAN controller data sheets to indicate that in this communication media, which is based on message addressing, you have a very interesting attribute, the so-called CAN identifier, that identifies in CAN Classic the priority as well as the data content. Exists in two formats, the 11-bit and the 29-bit identifier, and typically in CAN controller data sheets, this indicates that they are capable to run both addressing formats. Yeah, this specification was then submitted to ISO, and in 1993 there appeared the first CAN standard, ISO 11898, which covered that, what we call today CAN Classic, the protocol, and the high-speed transceiver. So in 2003, this document had been revised and was split in two parts. A first part that is dealing with the data link layer and the physical coding sublayer, and the second part that covers the high-speed physical medium attachment, so what we call more or less the transceiver. We have there also the test plans, so the automotive industry wants to use tested components, so therefore we have standardized test plans in the document 16845. Around this standard series was extended by further functionality, but for the moment we just focus that when CAN-FD came up, there was the discussion where to standardize CAN-FD now, and after some discussions the result was why not merging CAN-FD and CAN-CC to the same international standard. And so since 2015 and 16 we have now our ISO 11898-1 and 2 specification standard series covering CAN-CC and CAN-FD, and we updated the test plans. And finally, since 2024, so since spring of this year, we have now the ISO 11898-1 and 2. The part 1 covers the CAN Classic, CAN-FD, and CAN XL data link layer. And the part 2 introduces some new terms, but in general it covers still the high-speed physical medium attachment, but also a physical layer more suitable for CAN-FD, the CAN-SIC, as well as the SIC CAN XL physical medium attachment sublayer implementation. So this means I have a certain flexibility. Holger will tell us about this later on, to optimize the communication also on the physical layer level to end up in a real, let's say, super speed mode in CAN-based communication. So why was all this necessary? So we see here a little bit the development of in-vehicle networks. So we see here some legacy networks which were installed at the beginning of this millennium. And we see here, okay, we had a CAN network for dedicated tasks, so for comfort, body electronics, so for controlling the drivetrain, the motor management, and automotive networking is typically a subject that is very cost sensitive. So therefore, the car makers evaluate also at the lower end, can we save costs on a certain to a certain extent, maybe at the lower end. Therefore, sometimes CAN is complemented by LIN, the local interconnect network, or there are some other tasks where you need a little bit more performance, maybe for multimedia applications. CAN, as the name said, is a controller area network designed for starting, stopping applications, communicating in a robust and reliable way a certain analog value. But CAN has never ever been designed for data streaming. So therefore, maybe other communication techniques for multimedia applications have been used. But the complexity in automotive networking increased. So therefore, the next step was to shift to a so-called domain-oriented in-vehicle network architecture. So you have not just a single CAN network for the body control, for the control of the chassis electronic and so on, but you have entire heterogeneous networks. And all of these domains are controlled by a so-called domain controller, and they have to synchronize somehow their process images via very fast communication links via automotive Ethernet. So you see very complex architectures, and in this design you have a disadvantage that you have to place cross wires across the car, so maybe to network all the electronic control units for the braking or for other applications, and therefore there was also some idea to future network architecture we will have soon. And furthermore, you can see, or you can simply assess that approaches like that are very communication demanding. So we had here an insight from Mercedes, which showed us via several generations of CAN networking in the Mercedes E-Class, how straightforward the amount of ECUs was increased and how the amount of messages needed to communicate in such a car more or less exploded. So therefore, it was very soon clear, okay, we have to increase the data throughput in CAN-based networks, or in automotive networking in general. And one step in this direction was the CAN with flexible data rate, so to allow a higher data throughput. And the development took place in a way that the major attributes of classic CAN, CAN Classic, should be kept. So as the design simplicity, to have a high reliability and robustness, and on the other hand, the data throughput should be extended. Unfortunately, one major attribute that reduces the configuration effort to a minimum, the priority management of the CAN messages in the CAN identifier demands a so-called in-bit time response, which is also, unfortunately, a limiting factor in the speed and brings the CAN Classic to those speeds that you may know today if you are a CAN Classic user. But as soon as it is negotiated who is the sender, you don't have anymore a so-called in-bit time response that tells you, hey, there's another outside who has a high prior message. Then it is clear who is the sender, and you enter up a certain streaming phase. In this streaming phase, you can turn up the speed to what your physical layer is capable to drive. And after you have transmitted more or less your data, then you have at the end of a CAN communication the acknowledgement to be sure that at least someone has received your data correctly. And in this acknowledgement, once again, we have an in-bit time response, and therefore we have the same restrictions as at the beginning of the CAN frame. And this means in between we can transmit with a higher data rate, and we can increase the amount of accelerated transmitted bits as we lengthen the data field. So Holger will show this in a CAN frame comparison. So for the moment, we just see, okay, we can accelerate in CAN with flexible data rate for the transmission of the data. So we had now with CAN-FD the possibility to transmit a higher data throughput, but as I've said, domain-oriented architectures have the disadvantage that you need a high cabling effort, and to reduce this cabling effort, there's a next transition in in-vehicle network design. It's the so-called zonal architecture. You have just zone controllers, and they integrate via some cabling all electronic control units that are occasionally next to them, and then they collect all the data and update the process image with the other zone controllers that on a higher level you can run the entire application. And this means also some requirements to the data. The data has to be somehow self-descriptive. You have to know from which area, from which sensor, from which electronic control unit is this data derived, under which condition was it measured or generated, to which kind of application does this data belong. So all these things that you also know from cloud computing are now also applicable in this zonal architecture. So you put a lot of more requirements on the way you communicate in the embedded networks. So this is more or less the driver for the development of CAN XL. Prior to come to this CAN XL, I like to mention that also some improvements at the lower end in CAN-FD communication were introduced. If you have to integrate, for example, a lot of simple devices, let's say, you can also have a cost-sensitive solution. It's the CAN-FD Lite communication that had been invented. So CAN-FD Lite is intended for use in deeply embedded, price-sensitive sensor actor networks. So the necessity for a lightweight CAN-FD network became evident during the development of systems for modern car lights. The connected LED clusters are controlled individually by one commander node. The communication follows a commander-responder schema, and the responder nodes do not support network arbitration. They only transmit CAN-FD data frames on request of the CAN-FD Lite commander. So accurate clock source at each node is not required. So this means there's a lower cost and improves the implementation reliability. Yeah, so nevertheless, we think about high data throughputs also. So therefore, we have some additional requirements derived from the zonal architecture. So we want to have scalable networks regarding bitrate, data length, data throughput. We want to integrate legacy approaches. We need to think about, therefore, on multiple higher layer protocols running on the same cable. If we are very connected to the Ethernet world, to the cloud, then we have also the task to map or tunnel Ethernet frames. And on the other hand, we want to keep all the well-known and beloved attributes of CAN Classic, that we have a robust communication, a reliable communication, and hardware and software that is available for reasonable prices. Yeah, the insight to CAN XL, which is then the answer to all these requirements, is then provided by Holger. Holger, please.
Okay, thank you, Rainer, for the basic introduction. And we're going now a little bit into some more details. But the real details will be provided in the next presentations. Just a few features of the CAN XL data link layer. We are backwards compatible to CAN FD. This was an important issue which we learned when we moved from CAN CC to CAN FD. We have now splitted the functionality of the priority identifier, so in an 11-bit identifier indicating the priority of the frame. It's not indicating anymore the content. The content is separated by a 32-bit value, the so-called address field, and where we can have then the indication what is in the payload in the 2048 bytes. We also have in addition some functions like the virtual CAN network ID. This is can be used to indicate what kind of networks you have in mind, as you can group then the different frames transmitted to different virtual CAN network IDs, so you can run different applications in parallel on the same cable. What we have also done is that we have a cascaded CRC, and which we can achieve a true Hamming distance of 6. A Hamming distance of 6 is able to detect 5 randomly distributed bit errors. The 11-bit stuff bit rule is not more related to the, we have now not more fixed stuff bits, and this is an improvement to achieve that. We have also in the stuff bit counter as in CAN FD, and just integrated into the CRC field. The start of frame bit, the end of frame is the very same as in CAN Classic and CAN FD. Rainer has mentioned this already, that we have in the arbitration phase the very same behavior in all 3 kind of CAN data link layer protocols. A new feature is also this service data unit type field, which indicates what is the next higher layer protocol. This is similar to the Ethernet type field, so we can distinguish between different applications. Combined with the virtual network ID, we have 2 times 16-bit, where we can indicate which type of higher layer protocols we support, and we have instances of this by means of the virtual CAN network ID. We support, of course, CAN hour frames, but we do not support CAN remote frames with CAN XL. Here you see the 3 different data formats for the different CAN protocols. On top you see the classic CAN, which you may know with the start of frame bit, arbitration field, control field, data field, CRC, acknowledge field, and the end of frame and the interframe space. The CAN FD frame format looks very similar, but there are some differences regarding the speed, where we have the arbitration phase with the limitation to 1 megabit per second, and then we go into the data phase where we can accelerate the speed, and this is in the middle of the control field, and at the end of the CRC field we are slowing down again to the arbitration phase with the 1 megabit restrictions. However, we have 64-byte in the data field, and this and the faster speed, this means we have higher throughput. In CAN XL we have some more. It's the same like in CAN FD. We have the arbitration phase and we have the data phase, but we have also these additional fields like VCID and the the other things which we have introduced in the control field. Of course, we have an improved capability to detect errors, bit errors by means of these two CRC fields. In the beginning, the field CRC, and then we have the frame CRC. So going a little bit into the MAC frame of CAN XL protocol to see the different possibilities which we have there. You see the data link layer protocol unit starting with the starter frame bit. Then we have an arbitration field with 15-bit, including the priority ID, including a reserve bit, including an extension bit, including an FDF bit, and the XLF, indicating that this is a CAN XL MAC frame. Later on, then there we come the control field. The control field has a 4-bit field where you change the speed from the arbitration phase to the data phase. We need 4 bits for that, and we do the transition from one speed grade to the other speed grade by means of 2 steps. And after that, we have the new higher speed. Then we transmit the service data unit type, and this is an 8-bit field indicating that you're using, for example, a transport protocol or a J9039 approach or a CAN open approach. This is followed by the SEC bit. The SEC bit indicate that you have additional function implemented, like frame fragmentation or cybersecurity, things like CANSEC, which is under development. Then this following the data length code, and the data length code is extended to 11-bit in order to address or to indicate that you have up to 2048 byte in the payload. Then we have additionally the SBC field with 3 bits, where we can indicate that we have detected something like the bit counting for the different bits. And we have then the PCRC, this which is the preface CRC, protecting the already transmitted bits. After that, we have the virtual CAN network ID. As I said, this is used to indicate different in parallel running applications. And then there's following in the control field the AF field, which indicates the content of the following data field. The CRC field has also is then following the second CRC, which is cascaded with the first one, so we can really achieve a Hamming distance of 6. This is the frame CRC, and then we can, after that, or we have to slow down again by means of the ACK field, also in a 2-step approach. We then go back to the arbitration phase speed, which is 1 megabit per second. And of course, the end of frame field is the very same as in classic CAN as well as CAN FD. Just a small summary of the differences between the 3 protocol variants. In the payload length is different. You see, we are limited in classical CAN to 8 byte. We are limited to 64 byte in CAN FD, and in CAN XL, the limit is 2048 byte. This means we are larger than any Ethernet frame. And so we can map also Ethernet frames into a CAN XL data frame. The priority identifier is in the 11 or the 29-bit identifier in CAN CC and CAN FD the same. So we are double using this field for 2 different purposes, to indicate the priority and to indicate the addressing. In CAN XL, we have separated these 2 functions. One is in the 11-bit priority ID field, and the acceptance field, which is the 32-bit field. This indicates the content of the what is in the data field. The service data unit type field, an 8-bit field, as well as the virtual CAN network identifier field, is also an 8-bit field. Both are new and are not available in CAN-CC and CAN-FD. This makes CAN-XL suitable for more complex applications, where we can run different applications on the same cable. This means also that we have the possibility to have multi-networks connected easily, and we can run in parallel different applications on the same cable. This is important for any backbone application, because if we have a backbone, then you might have logical networks running on the same cable. The bit stuffing is dynamic in a classical CAN and dynamic with fixed in the CRC field for the CAN-FD protocol, and in CAN-XL, anything is dynamic in the arbitration field and fixed in the data field, in the data phase fields. The CRC polynomial is 15-bit in CAN Classic CAN, and 17 and 21 in CAN-FD. And in CAN-XL, we have 2 CRCs, one 13-bit CRC in the prephase, and we have 32-bit in the frame protection. Error signaling is always on in CAN-CC and CAN-FD. However, in CAN-XL, we have the option to switch off the error signaling. Then we can achieve higher bit rates, and we can go up to 20 megabit per second. This is also the same for the fast mode. Fast mode switch is not available in CAN-CC and CAN-FD, but in CAN-XL, we can enable the fast mode for transceivers capable to support that, so that configuration is being done by the system designer. The bit rate in the arbitration phase is always 1 megabit per second, all 3 variants of the protocol. In the data phase, which is not available in CAN-CC, you can also only run 1 megabit per second. In the data phase of CAN-FD, you can run up to 8 megabit if you're using so-called SiC transceivers. SiC transceivers are transceivers capable to suppress ringing on the bus lines. And as I said, in the data phase for CAN-XL, you can run up to 20 megabit per second if you're using CAN SiC XL transceivers for that purpose. So, as I said, there's the possibility of the support of multiple higher layers on the same cable. This is an important new feature, and this needs to be discussed how we can use it in an optimized way. Mainly this is done by the SDT field, indicating that this is a CAN open message, or this is a message for J9039 or any other higher layer protocol which is standardized. What we can achieve with the you see it on this slide. This slide was originated from Bosch. You see that we can have a much higher XL data phase bit rate, 60 megabit per second. If you run this, then you have a lot of throughput. The throughput is then the net bit rate is then 14 megabit per second. And if you're looking where the classical CAN is, this is very at the lower end, and we're nearly to the 0. So we can really improve our data throughput with CAN-XL. So there are different implementations available for the CAN transceivers. We have the high-speed transceiver with the non-return 0 coding, and you know this, it's limited to 1 megabit per second. CAN-FD transceivers, they are capable to run 2 megabits and more, depending on the design of the network. CAN-SiC transceivers with the signal improvement capability, also using the NRZ coding, they allow to go up to 8 megabit per second. But we have some limitations in the arbitration bit rate to 66.7 kilobit per second, which can be overcome, but only when you restrict the use of the identifiers. CAN SiC XL, they have dual mode transmission with PMW coding, and we can go up to 20 megabit per second also here. we have restrictions regarding the arbitration bitrate to 667 kilobit per second. So this shows you the ringing suppression capability.
I'm sorry to interrupt, Mr. Zelt, but it looks like we are almost out of time. So,
okay.
So will you do a brief summary of your speech, or?
I will do a brief summary with that.
Okay, thank you.
So the summary is CAN is still a valid technology, and various CAN users can use it depending on their requirements. And if you still, and we will still see a lot of CAN classic applications, and in the automotive industry moving strongly in the moment to CAN FD, and the next step will be then CAN XL. And you can use it easily as a backbone network, also in some commercial vehicles or in other applications. And CAN XL allows new higher layer functions that support the system designer, especially for those which have different applications running on the same cable, or want to run different applications on the same cable. Of course, we're also discussing how we can use the Ethernet software on CAN XL, and also this is possible. But then we use the robustness and the reliability of the CAN data link layer for those applications originally based on TCP, UDP, or some higher layer protocols like SUMIP. So this is my brief summary. Just if you want to contact us, you can have, you will see that we have different email addresses, and then you can send your requests to us. Thank you.
Okay, thank you so much for the wonderful presentation. Just due to the time constraints, so we have to move on to the next speech. But don't worry, we will leave some time for the questions at the end of the webinar, and we have collected some questions during your speech. 那么好的，谢谢这个讲师的这个演讲。那么其实由于时间的原因的话，我们在这一个环节上的一个 Q&A 环节，暂时的话我们就会先取消，但是大家不用担心啊，因为在研讨会的最后，其实我们会给大家预留一个整体的 Q&A 的环节，然后刚刚大家在演讲过程中，然后提出来的问题我们都已经收集好了，发给了我们的讲师，然后最后的环节上我们会选出一部分问题进行解答，然后同时呢，我们的工程师也会把自己能够应付的一些问题帮助大家解答，已经回复在了我们的直播的评论区里面，大家也可以去看一看。那么接下来的第二场演讲呢，是由博士的首席技术专家 Dr. Arthur Muller 带来的。然后 CAN XL， 因为大家都知道 CAN XL 技术是博士的专利，他们对于 CAN XL 技术发展起到了关键的作用。那么接下来的话，就有请亚斯博士为我们带来 CAN XL 面向未来的电子电器架构推动者的相关演讲。So Dr. Muller, please begin your presentation.
Hello, so thank you very much for the introduction. Can you hear me?
Yeah, very clear.
Very good. Thank you very much. So I'm proud to be part of this webinar, and I'm happy that we have so many followers and listeners. And as the previous presentation, I want to quickly introduce myself. So I have 14 years of CAN experience now, because since I started at Bosch, I was working on CAN, and I started with CAN FD. And currently at Bosch, I'm responsible for the standardization of CAN XL. And my current task at CiA, at CAN Automation, is that I'm the chairman of the group that specifies CAN XL, and not just CAN XL itself, but also the things around CAN XL. So not just the protocol, but everything what is needed to run a CAN XL network. And my presentation today will be about CAN XL, so I will focus here, and I will show you why CAN XL is an enabler for future-proof EE architectures in the car. And before we start, I also would like to start with a little bit of history, like the presentation before, but I only have one slide to that, and I will visualize this. So when we talk about CAN evolution, then I will highlight now the CAN transceiver part. Here you see on the light. Let me turn on the laser pointer. We will focus on the transceiver part and on the protocol. And you see, in 1990, the first products for CAN Classic came to the market and were adopted, as said before, in the Mercedes S-Class as first user. And this was perfect for a very long time. You see, only 25 years later, roughly, the need came up to have something faster. And at that time, the first product for CAN FD came to the market. And as you know, now most cars on this world use CAN FD already in the car. And what means CAN FD? You probably know it very well. CAN FD means a very small change to classical CAN. It means a higher or longer payload. So instead of 8 bytes, 64, and an improved speed. You see, with a new transceiver called CAN FD transceiver, you can achieve a speed up to 2 megabit. But somehow the people wanted more, so they were a little bit disappointed that CAN FD only supports 2 megabit with the FD transceiver, and so the transceiver people went on thinking about how to build a better transceiver, and therefore quickly later, only 3 years later, the first SiC transceivers came to the market. SiC stands for Signal Improvement Capability. The previous presentation showed an impressive picture how SiC can damp the ringing and so improve the signal quality on the wire. The CAN FD protocol, as you see, was not changed, so this is just another option for the transceiver here. And then already quickly later, you see in 2023, so last year, the first product for CAN XL came to the market. And CAN XL is now a big jump compared to CAN FD. And as mentioned in the previous presentation, we have a longer payload, but additionally to that, we also have security, we can support Ethernet tunneling and other things. And to not just improve the protocol, we also developed a new transceiver, the so-called SiC XL transceiver, and you see already the similarity in the name. So it's a SiC transceiver with some additional feature, because SiC is already very good, so we just extended it. And this SiC XL transceiver can achieve up to 20 megabit. And it can really achieve it. I will show you later how and when it can achieve it. So my talk today will be about CAN XL, but as also mentioned by Holger before, and Rainer, there is a second trend in the CAN community, as well as in the Ethernet community. There is also a trend for very, very cheap and light devices for very simple end nodes to control LEDs and actuators and so on. And so this is the CAN FD Lite. CAN FD Lite means it's the CAN protocol, but there were some features removed to make it cheaper. So it's fully compatible to CAN FD, you can use the same tools and so on, but it cannot support some of the features, for example, arbitration. It cannot support 29-bit IDs, and by that we can reduce the price of CAN FD by 50% approximately, and this is a lot because CAN FD is already cheap. And you see CAN FD Lite can be also used with any type of transceiver that is available for CAN. So my today's presentation will be about CAN XL and about this pillar, and we will go into the deep, not so deep, but we will look at the specific important features. So let's now have a look on the agenda. So I will talk about standardization and availability. I saw already in the chat were questions regarding availability of parts. I will talk about layer 2 and layer 1. So layer 2 key features, what can the protocol do? What is the specialty? And what options do you have on layer 1 on the transceiver side, and what is the performance of the transceiver and the maturity? And at the end, I will talk about some additional functions like security that are also needed in real networks, right? So just a longer payload is not sufficient for future networks. So let's start with standardization and availability. It's a challenge for me a little bit because I have Chinese slides and I don't know what is written there. I need to remember. Okay, standardization and availability. So we are very happy that after a long, hard work, now the ISO standards that specify CAN XL and the new SiC XL transceiver are now finally released. The technical background and the specification at Canon Automation was stable since a long time, but as you know, to standardize something at an international standardization organization just takes time and patience, and I'm so happy that we succeeded, and in May this year, the standards were released, and as you see here, the standard for the CAN protocol contains all CAN protocols, so the classical CAN and FD without any change, and 2 new things were added, CAN XL and FD Lite responder. And on the transceiver side, we also have the high-speed CAN and CAN FD transceivers unchanged, and the SiC transceivers XL transceivers. Incredibly important to bring stability because they cannot be changed quickly. So everybody knows this is the status and this can be used now. And when you have standards, you have a broad availability. But we need to make sure that what is written down on these papers is really functional. And to make that sure, we worked very hard and we made so-called plugfests. And this is a picture from the first CAN XL plugfest where we tested the components. So plugfest means we meet together, the engineers from the different companies, bring our implementations, plug them together and test if they are interoperable, if they are functional. We see problems and then we fix it and then we come back and test them again. And you see this plugfest was during Corona times in 2021 when the first implementations were available. And already at that plugfest, we could achieve in a star topology a 20 megabit communication. And since then, we had many more plugfests. And you see the first one was on the left top, and then we had the second one, and the third one, and the fourth one. And you see the number of people increases and increases. And there are a lot of wires on the tables, and all plugfests run successfully. So it was a very positive event. And the last plugfest was in May this year in Baden-Baden, the day after the International CAN conference, because then anyway everybody was there. And the plugfest was so big that it was even difficult to organize it. We had about 50 participants, 50. And you see that we have had a track A, track 1. And in this track 1, we focused on layer 1 and layer 2. So on the CAN protocol and the transceiver with a lot of cables and so on, oscilloscopes, a lot of engineers from all over the world, from India and from other countries. And here we were testing, for example, 2 new microcontrollers, one from NXP and one from ST Microelectronics that were never brought to plugfest. And on the right side, we see the track 2, so a parallel track that is much smaller, where just 3 companies attended, Bosch, Volkswagen, and Vector. And here they tested fragmentation, which is an additional function in CAN XL. I will talk about it later, what it means, fragmentation, and why this is important. And on this plugfest, they showed that the fragmentation that we specified is functional. And so now we know it's functional, it's specified, and now we can release the specification at Canon Automation. And this is currently done. So you see, this was the last plugfest, and if needed, further plugfests will be organized in the future. Plugfests are important, but we still need parts. To build cars, you need parts, right? So another question is, what is the availability of parts? And when we talk about availability, we need to be a little bit more selective. We need to think about availability of what? And here you see a picture. We need, in the first step, the so-called CAN XL IP. IP is the intellectual property. This is the hardware implementation, or just a circuit that will be later integrated in a microcontroller. So this is the so-called CAN controller. And then we need a microcontroller or some chip that integrates this digital hardware. Then we need transceivers. In this case, SiC XL transceivers to operate the CAN bus at a high bitrate. And then we need tooling and software and other things. And now let's have a look on the availability. And this is what is available today. We see regarding the CAN XL IP, we have some from Bosch, but also from other companies. Some companies only implement them for their own use, some others sell it, some sell it for microcontrollers, some sell it only for FPGAs, but there is a big choice. There is also verification IP for people who want to implement an IP module. They can buy a verification IP and can test if their IP is working properly. So it's about simulation and verification. Then when we look on the microcontroller market, we see the four big players from the Western world, Infineon, NXP, STM, and Renesas, have microcontrollers with CAN XL, and they will have more and more over the time. And I'm very happy to say that very soon I will extend this list with a few microcontroller manufacturers from China, because CAN XL will be very soon also in Chinese microcontrollers. Regarding transceivers, we have product announcements from three companies. This is TI with an 8-pin transceiver, from Bosch with an 8-pin transceiver, and from NXP with a 14-pin transceiver. And besides that, Bosch and NXP also have concept silicons. That means some implementation to prove that we really can master the technology and it really works at 20 megabit. And on tooling and software side, you see tooling is available. For example, very soon from Peak, for example, and so on. Oscilloscopes also already support decoding of CAN XL frames, and there is also an evaluation board available from C&S. So who wants to explore the performance of the physical layer, he can already start today. And there are other things that are important. For example, CAN XL is fully supported by AUTOSAR. And the important thing is by Classic platform and by the adaptive platform of AUTOSAR. CAN XL is inside there. We already start to have software related to CAN XL. And the funny thing is, CAN XL can tunnel Ethernet, but also Ethernet can tunnel CAN XL. So you see the two worlds, Ethernet and CAN, which are important in the car, can tunnel each other, so they can have a very good coexistence in the car. So the clear message is here, parts are available and they are getting more and more every day. So CAN XL is ready to use. Now, so far to standardization and availability. Now let's move on to have a look on the CAN XL key features. And here we have first a look on the protocol. And on the protocol, as mentioned in the previous talk, here I list the core features, right? The most important ones. There are many more, but these are the most important. So CAN FD and CAN XL have some similarity, and this is that they both have 2 bit rates. One for the arbitration, this is this one, which is still limited to 1 megabit. And the other bit rate is for the data phase. And this is now configurable from 0 actually, but 0 doesn't look good here, so I wrote a 1, from 0 actually to 20 megabit. And for sure, the bitrate that you can configure depends on the transceiver you use and the topology you have. So you can not always have 20 megabit, only when you have a good design. Regarding the payload, we have here now 1 to 2048 byte payload, and this can be now used for any application. That means you can use CAN XL as in the past you used CAN FD. So for small frames, for signal-oriented communication to transport some pressures and speeds and so on, where you need maybe just frames with 100 byte or less. But you can also use CAN XL for IP-based communication to support the modern protocols like some IP and so on. So by having this large payload, there is no excuse now anymore why something is not working. Everything is possible. So it should never be changed again. And CAN XL is not just faster and bigger. CAN XL has also several more features, like showed in the previous presentation, like virtual networking, 2 powerful CRCs that protect the frame, and so on. When we would like to represent a CAN XL frame visually, then it would be probably the following picture. We have an arbitration phase that is slow, but also very short. We took care that this is really short to not waste bandwidth on the bus, because the bits are slow. And then we have a fast and potentially very big data phase in the middle. And at the end, we again have a slow but short arbitration phase at the end, because here in the end of the frame, you know, there is the famous acknowledge bit that in CAN XL is still available. So far to the core features. But there was already a question in the chat, which was, okay, what else can CAN XL do? And one super important feature is that CAN XL and CAN FD are compatible. And now the question is, okay, they are compatible. What does this mean? And how does this work? And I want to show you this now. So technically, this works the following. Technically, CAN FD, that is today in the cars, is able to ignore CAN XL. So this is already a feature of CAN FD, that it can ignore CAN XL. And we built this into the CAN FD protocol because we suffered, when we introduced CAN FD, that the classical CAN nodes destroy the CAN FD frames. So we didn't want to make the same mistake again. And then we said, okay, CAN FD gets a compatibility mode. It is able to ignore a new protocol, CAN XL. And this is recognized by a bit in the frame. So it's a clear and robust way how this works. CAN XL, on the other side, is bilingual. So he can talk 2 languages, like Chinese and English. So the CAN XL node can understand both. And this compatibility is limited to 8 megabit. And the reason for that is that beyond 8 megabit, we need to use the new transceivers for CAN XL. And the new transceivers have different voltage levels, and they are not backward compatible. So therefore, there is a small limitation here. And this is how it can look like in a network. So it looks like we have 2 CAN FD nodes here that communicate with FD transceivers and 2 megabit. And then we have 3 CAN XL nodes, and they use probably SIG transceivers, and so they can use 5 megabit. And now you may wonder, how can the one node talk with 5 megabit and the other one just with 2? And the reason is very simple. If you don't understand the other language, so FD node doesn't understand XL, then you don't care how fast it speaks. So the only condition that has to be fulfilled is the speed has to be so slow that FD nodes still see edges. So as long as the FD node can see an edge, he knows, okay, there is something on the bus, and he keeps waiting until the bus gets idle. And there is now a clear benefit for the customer, and the benefit is that he can use the cables for both, for CAN XL and for CAN FD ECUs, and this allows him also to do an incremental upgrade. So he can introduce CAN XL step by step while not replacing everything. And this is, from our point of view, an important feature. But not enough. CAN XL can do more. Like I mentioned already, we can tunnel Ethernet. And what means that? Tunneling Ethernet means that by tunneling Ethernet, we inherit, so we take the whole Ethernet world and can bring it to any ECU that supports CAN XL. So we can do service-oriented communication, whatever we want. But how does this work? So like in the previous presentation mentioned, the CAN XL frame, which is the orange block here, has a field called SDT. SDT is the service data unit type. And the SDT field tells us what is inside the payload. And the values for this SDT field are specified in a CiA document. And the value 5 is specified to mean there is an Ethernet frame inside the payload of the CAN XL frame. So everybody can know and see it. And AUTOSAR supports AUTOSAR supports the CI 611-1 document, so the Ethernet tunneling fully. So this is fully standardized. And so this could look now in a real setup in the following. You see here on the right side a zone architecture. So we are zooming in into a zone. This is a zone ECU that is connected to an Ethernet backbone. And on this zone, we have different ECUs that have nothing to do with each other. We have an FD ECU that can only understand FD. We have 3 XL ECUs that do maybe some radar application. And we have some ECU that needs to do some XL communication, but at the same time also Ethernet communication. And this works now the following. So when a frame is forwarded from the zone ECU that contains an Ethernet frame, so this frame is received by this node, and it is received with the normal CAN transceiver, with the normal CAN protocol, so everything is normal. Only in the software driver, it is checked what is the value of this SDT field. And if the value is 5, which means an Ethernet frame is inside, then the driver removes this orange part, which is the CAN XL part. These are just a few bytes of data. And then it forwards this Ethernet frame, what is in the payload, on an interface, on the Ethernet interface. And the application sitting here above doesn't even know that there is no real Ethernet hardware below. So CAN XL can be used as better physical layer for Ethernet. And for sure, this interface will have a virtual MAC address. And all other frames that have a different SDT value will be forwarded to this other interface. So by this, there is a clear benefit for the customer because you can use 3 types of protocols, FD, CAN XL, and Ethernet over XL on the same piece of cable that brings you big flexibility and also cost saving. So far now to the protocol features. Now let's have a look on the physical layer. On the physical layer, the first question I typically get is, which transceivers can I use with CAN XL? And the answer is very simple. You can use all transceivers with CAN XL, really all. And what means all? It was already shown in the previous presentation. This is high-speed CAN, FD, SIG, or SIG XL transceivers. And there is a very good thing. And the good thing is that all transceivers are pin compatible. So you can decide later when you solder your transceiver on the board which you want to use, because they are all pin compatible, so you have full flexibility anytime. And another good thing is the price of the microcontroller is the same, independent if there is just classical CAN supported FD or CAN XL by the micro. So the price is only defined by the transceiver, by the analog part that you solder on your PCB. So you can have CAN XL. So there is a chat, and they're asking me something. I need to stop presentation mode. I need to check what is going on in the chat. Maybe something. Okay, it just seems to be some questions, so I will continue my presentation. Sorry for the interruption. Okay. So the point is, the price of your network is only defined by the transceiver. When you pick an FD transceiver for CAN XL, then you can have CAN XL at the price of CAN FD. Now, the big question is, okay, we promise you 20 megabits here, but when can you achieve these 20 megabits? Always, just sometimes, and in which topologies. And to figure out this, we analyze this. We analyze this with help of many companies, Infineon, NXP, Bosch, Mercedes, Volkswagen, and some more. And we did it the following way. We defined a set of topologies, going from simple topology, point to point, over daisy chain, a linear topology with short stubs, then a linear topology with some big cable in between, and then a topology with long stubs, star, double star. So you see the topology gets more and more complex. And we calculated this, we simulated this, and we also set up the network in reality in the lab together, and we tested it. And we came to the following results. As long as you use a simple topology, that means point-to-point, daisy chain, or linear, you can achieve 20 megabit. And when you start making your topology worse by making it very long or having stars, then you see your data rate will decrease, or your bit rate will decrease to maybe 15 megabit or less. And even 360 meters are possible at 2 megabit, because you might wonder why did we test that, but on ships, so that means in maritime applications, they have very, very long cables, but they need only very low bit rates. So they are interested in low bit rates with CAN XL. So far to that, but this is not enough yet, because we need to test also if CAN XL works in a real car. And luckily, for the Volkswagen Group did this. The Volkswagen Group was following the CAN XL standardization. They even started it by a request. They followed it now since 4.5 years, and they invest a lot of time to check CAN XL if it's really working. And they presented their results now on the International CAN conference. And one presentation was from Marco Moch, where he presented about if CAN XL is applicable in the car at 20 megabit, and what are the benefits. And this was his conclusion. Yes, 20 megabit in a real car works. And he said, it really works. And so this is a very positive message, because they did it on car level, right? So they didn't do it in the lab, really in the car. But there is another important message that I want to give you, because there was a second presentation from Volkswagen, and they analyzed the EMC performance of CAN XL in the car, because this is also very important. Otherwise, we'll never get into the car when this is bad. And there was also a clear message that both the EMC, so the emission, so the radiation of the transceivers that they analyzed were good, and also the immunity, so the robustness was also good. And so they were satisfied with that, and so this is a very good result for CAN XL on car level already. So it's not just a dream, it's reality. It will work in the car at high bit rate. So far to the transceiver. Now let's have a look on the last few slides, and I will highlight here the additional functions. And higher bit rate, tunneling Ethernet, longer payload, these are all essential functions. However, it is not enough. It is not enough for future-proof networks, and therefore we have additional functions. Because in some use cases, not in all, you need them. And one additional function is, for example, time synchronization. And the very essential ingredient for time synchronization is the timestamp, because you need to do time stamping, then you know when the packet arrived, and then you can do with help of the timestamp the time synchronization. And we made sure that the ISO standard contains that CAN XL nodes capture 64-bit timestamps for all transmitted and all received frames. So from timestamp point of view, we are safe. But now the question is, which time synchronization algorithms can we use? And we worked on the topic in the last year at CAN Automation in a working group with many experts. And we came to the conclusion that the existing time synchronization protocols are sufficient to be used with CAN XL. So we do not need to change anything. We can just reuse what exists. And we can reuse the AUTOSAR CAN time synchronization protocol, but also the AUTOSAR Ethernet time synchronization protocol when we tunnel Ethernet frames. Then we just can reuse it. And The first option here you see we can use in mixed networks, because here for time synchronization we just can use an FT frame. So the CAN XL node would just send an FT frame and it works. This is mature technology, nothing has to be done. The other three variants you see with the XL frames, they work on paper. Everybody said, yes, for sure, this will work. But in a real environment, they will be now tested by Vector. They will do a proof of concept to really prove that it works. So the question of time synchronization, I consider as solved, as we have a good solution for it. Another thing is security. Some communications require security. And security is already available for sure, not always used, but available. For example, on application level, there is SecOC, the secure onboard communication that is applicable to Ethernet, CAN, FlexRay, to every protocol. Then we have some specific security solutions that are only applicable to Ethernet, TLS, IPsec on layer 3, or MACsec on layer 2. And we saw that layer 2 security in Ethernet is very favored. So people like it very much because it's very easy to secure maybe 10 links in the car, but it's very hard to secure 100 communication relationships in the car. So people are favoring layer 2 security, and we also see this, and therefore we also specify a layer 2 security protocol for CAN. We call it CANsec, and it is from the features very similar to MACsec. The implementation is different, but the features are very similar to solve the same problem. And what is the status now? The status is that we have a data plane, which is the frame format and the cipher suits and all the security features. And we are very far with the specification already. We are at 95%. Only very simple things are missing, some configuration and so on. And we plan to finish this in the next year so that we can have products soon. And now let's have a look on the CANsec features. The CANsec features are integrity. That means we have some check value, integrity check value in the frame. So we know the data arrived without any change. Then we can encrypt, so we can provide confidentiality, and we provide replay protection. Replay protection means freshness. And these are the same features as also MACsec provides. In CANsec, we also have the choice for a lightweight crypto algorithm, so not just the expensive one, also a lightweight one. And we also optimize for multicast, because typically CAN is multicast, one sender, many receivers. So CANsec is not yet done, to summarize that, but we are very close to finish it. And Bosch will focus on this topic to finish the CANsec specification in CiA, to release the document. And now I come to the last slide and to the last add-on function that we have. And this is the so-called fragmentation. And fragmentation is necessary because we have a kind of a problem. When we use very low bit rates with very long frames, so example, at 10 megabit or at 8 megabit, you send a frame, a very long one. Here I show an example where we tunnel an Ethernet frame at 8 megabit. Then this frame occupies the CAN bus for 1.7 milliseconds. And this is relatively long. And this might be too long for real-time applications. And so we need to do something. And as you see, if you would make here 10 megabit out of it, it would be still 1.5 milliseconds. So the problem is the same in CAN and in 10BASE-T1S. However, we have now a solution for it in CAN XL. And our solution is fragmentation. We know that we are slow and we know that the frame is long. So let's split the frame in smaller pieces. And this is what we do. We send the frame not as one piece, but in several pieces, as several frames. And we reassemble it on the receiving side. And this is how it looks like. We have a bus with some frames on it. And here you see a long CAN XL frame start. And this high priority short XL frame wants to be transmitted here, but it cannot because the bus is already occupied. So it needs to wait a very long time until the long frame ends. And now with fragmentation, we can have the following scenario. So when the frame ABCD is sent in 4 fragments, in 4 pieces, then you see after the fragment A, this high priority frame can squeeze in, so it can be sent at least 1 millisecond earlier, and which then solves the problem. And the important thing is this fragmentation function is on the very low layer, on layer 2, and it is transparent to the application, so the application does not need to care about it. So, and so far now to the fragmentation, like I said, it was tested in the Plugfest, the specification is written, and now we will release the specification. And so I come to the end of my presentation, and I would like to summarize it in the following way. So CAN XL is the cost-efficient enabler for the zones, so for the last mile in future-proof EE architectures. And this is because CAN XL supports, so it's very powerful, it supports 20 megabit and also very long payload. It is very flexible, it can support a lot of different functions, different topologies, transceivers, and so on. So it's very flexible. It supports 3 types of traffic on the same piece of cable: CAN FD, CAN XL, and Ethernet over CAN XL. And additionally, it comes when it's necessary for an application with additional functions, which is security, time synchronization, and fragmentation. So thank you very much for your attention, and I'm happy to answer your questions.
Thank you so much, Dr. Mutter, for the wonderful presentation. And but I also think because of the time constraint, we don't have enough time to do a Q&A session. So we will compare the questions, organize them, and provide a comprehensive answer at the end of the event. And you also can check in the chat. A lot of our audience have some questions. We collect them in the chat, and you can see them, and you can answer them at the end of this event. 感谢亚瑟博士的分享，因为时间原因啊，可能这一次我们还是没有办法留出一个 Q&A 的时间，但是呢，我们会把刚刚各位所提出来的一些问题整理起来，并且做一个梳理，给出大家一个综合的回答。因为大家刚刚也发现了，有很多问题其实是重复的，或者说是一个比较综合的连贯的问题，所以一会儿我们的工程师帮亚瑟博士这边整理之后，最后在演讲的这个整个研讨会的最后，给大家一个比较综合的回答。然后接下来的演讲的话是即将开始，因为众所周知的话，英飞凌目前是在 CAN XL 的产品上有非常前沿的进展，我们也是非常荣幸的邀请到了相关的首席工程师。下面为大家带来演讲的话是英飞凌的汽车网络技术首席负责人 Magnus Maria Heller。Magnus 也是在CiA 协会的技术总监，他将为我们介绍 CAN XL 物理层的相关知识。那么有请 Mr. Magnus，you can start your presentation.
Okay. Hello, good afternoon. One question, can you see my presentation?
Yeah, I can see your presentation.
Thanks. Yeah, my focus here today is of the CAN XL physical layer part, and one of the first question is, what is a physical layer? Most of the people are thinking physical layer is only the wire or the transceiver or both together, but at the end, if you're going to higher bit rates, like in CAN XL, the physical layer starts really in the microcontroller. So there's here CAN controller, which is implemented in microcontroller, more or less starts transmitting frames, receiving bits, and for the CAN controller or for a microcontroller at the beginning, these are pulses, and they are walking through the microcontroller. And then the first physical layer, what you can see is here really the interface between the microcontroller and the transceiver, and it's not really. It's critical, not really critical, but you have to take a look on it. And it's not so relaxed like in the past with CAN FD and low bit rates. And then we have the transceiver, which is my main focus today. And also what you need are mode jokes. A lot of time I see that additional ESD components are used, and all these devices have an influence on the communication and the physical layer quality. And then we have the connectors, which are also very important. Meanwhile, if you're going to 20 megabit, then you have also to look on the quality of the connector, and at the end also on the quality of the cable. And for the cable, we have also an own CIA document, a CIA specification, that you have really a good wire for CAN XL communication with high bit rates. So if the bit and bytes from a protocol becomes voltage levels and timings, so then it's a physical layer, and really we have to look on all components here, what I have shown, not only on the transceiver and on the wiring harness. So my presentation today is for introduction a little bit the CAN physical layer basic requirements, and I will have a look on CAN 6, this new CAN FD transceiver device for signal improvement capability. And then this concept we're also using for CAN XL plus an additional mode for the CAN SiC XL transceiver. And then I will show how we manage this. And then you see also what Arthur has shown, a little bit which protocol variant you can combine with which transceiver. And also additional information about the CAN XL plug flash, also Arthur has shown before, and then at the end, my personal conclusion. But let us come at the beginning to the physical layer basics. So what is important for a physical layer? Yeah, the CAN concept is, or protocol concept is a concept which allows collision on the bus. You have this during the arbitration phase here, or you have it in case of an error frame scenario. So in this case, reliable signal has to be on the bus. No damage of devices on the bus is allowed. And that's the reason why the CAN transceiver can override the levels of other nodes. We call it dominant, and the other ones are recessive. And this allows us also that two nodes or more nodes can transmit data at the same time. Also, what is a feature of CAN? These typical star topologies, single star, multi-star, and really sometimes crazy kind of topologies. Everything is supported by CAN transceiver, independent if it is CAN, CAN XL, or CAN FD. A big feature of our CAN transceiver is that they are really absolutely robust against noise from outside. And also the opposite direction, we are really perfect. So the emission, if we transmit data, is really low. So we will not disturb anything. And this is the main function, let me say, disturbance and emission. These are the main function, the main features a CAN transceiver has. So the basic concept is really that one level dominates the bus and is really dominated by transceiver, and the recessive level is generated by the passive elements like a resistor on this bus. Here you see typical waveforms on top of a transceiver. You see here the TXT signal. Here you have really logical levels, 1 and 0. You see here the single-ended waveforms with CAN high and CAN low. And what is very important at the end is the differential signal. That's the difference between CAN high and CAN low. And if there is a difference above 0 volts, then we call it dominant. And this level is controlled by the transceiver. And then we switch back. And here this passive recessive phase is really dominated by all the resistors we have in the wiring harness. Here at the end, you see also how the transmitter output impedance behaves. So in case of a recessive level on the bus, the output impedance of the transmitter is really high. And then it goes down in a direction to 30 ohms. During the dominant phase, the impedance is very low and controls here the level on the bus. And then we are switching back to a high impedance phase. And yeah, here you see some numbers what we have. And at the end, this transition, dominant to recessive, this is the critical transition we have on the bus. This transition goes ringing because a wire prefers that they have always perfect matching of impedance here at the end of the wire, but we don't have. We have here impedance which is too low, and then we switch to impedance which is higher than the wire impedance. Then this causes ringing, and this reduces the maximum bitrate we can support on a wiring harness or on a CAN network. So at the beginning of CAN, 500 kilobit was really high. Then in the next step is CAN FD transceiver. The 2 megabit were really high, but it was not enough. So, and then a new transmitter concept was needed, and we call it SIC, signal improvement capability. And here is the transmitter impedance behavior again. So you see no difference here on the voltage levels on the bus, but you see here a difference in the impedance behavior. So the transition from dominant then to so-called medium impedance phase in a range of 100 ohm, which is close to the impedance of the wire, is now for a certain time implemented. And a certain time are normally up to 500 nanoseconds. If the recessive bit is 500 nanosecond and longer, or let me say recessive phase, because it can also be at higher bit rates that you have more than one recessive bit here. So the recessive phase, if the recessive phase is longer than 500 nanoseconds, or then we have this medium impedance phase, and then we switch to the high impedance phase again. And then collision is also possible like before. If the recessive bit is shorter than 500 nanoseconds, then the device will switch from medium impedance, which is called active recessive phase, to dominant during this active recessive phase directly. So here, due to this new active recessive phase, we reduce the ringing, and this allows us to go higher bit rates, to support higher bit rates, and here up to 8 megabit, sometimes more, are possible. Bit rates above 5 megabit most of the time are possible in point-to-point communication only, or a linear topology with short stubs. But most of the time, this transceiver is used for bit rates and networks up to 5 megabit. Also, you have an advantage that you can improve the reliability of huge networks to allow in these huge networks and 2 megabit. So here, everything or CAN-SIC can help you to increase in your existing networks also the maximum possible bit rate. Here you see again the differences. This is a CAN FD transceiver. You see here directly the impedance change from low to high, or from dominant to passive recessive. And in the SIC, we have now this active recessive phase. This is the difference between CAN FD transceiver and CAN-SIC transceiver, which at the end results in the support of higher bit rates in a network. Here you see an example. This was really measured in a network with 4 stubs. We have a center termination here. We have here unterminated transmitting node, and with a CAN FD transceiver, though the wire lengths were around about 5 meters each. And you see here that you have a huge ringing. Here's the dominant phase. Then we change to recessive, and then we have this ringing during and after the transition. And at the end, so for the receiver, you will see a long dominant phase, much longer than what is requested from the TXT side, and this reduces the recessive phase, and this limits the maximum bitrate. And here you see in the same network, we only replaced the CAN FD transceiver with the SIC transceiver, and then you see how it looks like. So that here the ringing is really small. It's above our receiver threshold, so the receiver sees only here dominant and here recessive, and with this suppression, or we can really increase the maximum bitrate in this network. Then, what's new in the CAN-SIC XL transceiver? So at first, this is the situation what we have at the moment. If you are using classical CAN, independent which IP you have implemented. So you can configure classical CAN IP and CAN FD IP and also CAN XL IP, and you can use here CAN FD, CAN SIG or CAN SIG XL transceiver. So if you have configured classical CAN with 500 kilobit, then the transceiver is always in the same mode. So only due to the toggling on TXT, the bitrate is faster or slower, but the transceiver is always in normal mode. That's the same if you're using CAN FD protocol. So, but the main difference here is in the arbitration phase, you might have up to 500 kilobit. And then the protocol handler increase the bitrate. So that means for the transceiver, the toggling on the TXT pin is faster. And at the end in the arbitration phase, switch back to 500 kilobit. So but the transceiver is always in the same mode. The transceiver changed nothing. Only toggling on TXT is faster. And this is the reason why we have higher bit rates on the bus. With CAN XL, you have now two scenarios. First one is you're using lower bit rates and only the SIG mode, which is implemented in the CAN SIG XL transceiver. Then you have the same situation like this CAN FD protocol. So the transceiver here limits the maximum possible bit rate. You have the CAN XL protocol on the bus, but the bit rate can be up to 8 megabit, and you have a transceiver which is always in normal mode only. So, and here you can also use the existing transceiver. Only the maximum limit here depends on the kind of transceiver. So with classical CAN transceiver, you will not achieve 8 megabit. Also with CAN FD transceiver, you will not achieve 8 megabit on the bus. So here the transceiver limits the maximum possible bit rate on the bus. And now we have the new feature in the CAN SIG XL transceiver to achieve 20 megabit. That means not only the protocol handler has to switch the bit rate, also the transceiver has to switch the mode to achieve on an existing network 20 megabit with the transmitter concept, which is used for CAN FD or classical CAN. 20 megabit are not possible, but with the new concept, which is close to FlexRay, can 20 megabit be achieved. And how this looks like on the bus, you can see here. So you have here at first the recessive phase. You have here an arbitration phase with 500 kilobit. You see here the signals for CAN high and CAN low with respect to ground. In yellow, you see the differential signal, and this is what you know. Yeah, really, you have here the typical waveform, 0 volt, 2 volt, so it's switching between 0 volt and 2 volt. And then here you see now it changes. And the concept is really that at the beginning, the transceiver changed the mode. And here the mode is called fast mode. And then the protocol handler increases the bit rate. And then you see it's a short frame at the end in the data phase, but in this data phase now you see how it looks if you transmit 20 megabit per second. At the end of this data phase, all switch back, the protocol handler to 500 kilobit and the transceiver back to SIG mode. So, and then you see here the end of the frame, and what is not shown here is acknowledge at the end. So this is now how it looks like on the bus. And you can directly see that here a SIG XL transceiver is used because here, especially on the differential signals, you can see that the transmitter mode was changed, and that here you can really receive also this kind of levels and pulses. We need a new receiver concept, why we have also changed the receiver. It's very simple. If you look on the existing concept for CAN FD and CAN SIG, so then we can have a low dominant level or we can have a high dominant level. The thresholds of the receiver, which is between 500 and 900 millivolt, are always the same. But due to this different level, also you get asymmetry, which also has an impact on the maximum possible bitrate on the bus. And this we have now changed. Now, in the fast mode, also the transceiver changed the receiver thresholds. And then we are 0 volt is the new threshold, and then we are symmetric, and also the asymmetry is very small. And here is also a part of the concept to achieve up to 20 megabit. Now, how we can change a transceiver from SiC mode into fast mode. And here you see it in this example. This is at the beginning the normal SiC mode. And now the information for a transmitter is what you see here. So here's the uncoded TXT level, like you see it with CAN-FD transceiver. And this is what you see if you have a CAN SiC XL transceiver. At first, normal levels, logic 1, logic 0, and then it's really fast. Then we have so-called PWM symbols. So in these symbols, also the level is coded. So this is here the transition phase. That's what I said at the beginning. The CAN XL controller switches the transceiver into fast mode, and then he transmit the fast mode, and then he switch back. So, and the transceiver is decoding these PWM symbols. As long he decodes the symbols, he is in fast mode. And when he is not able to receive PWM symbols, then he switch back into SiC mode. And this is now the concept. You see these symbols on all nodes, not only on the transmitting one, also on the receiving node, that the receiver thresholds will be switched from typically 700 millivolt to 500 millivolt. Also, Arthur has explained that you can combine now all protocol variants with all kind of transceiver. So, and the maximum bit rate, what can be achieved with CAN-FD and CAN XL transceivers on the one hand side, dependent on the kind of transceiver. So with CAN-FD transceiver, you can achieve up to 5 megabit. Normally it's used at 2 megabit. With CAN SiC, you can go to higher bit rates. But you should also be aware that the implementation in the microcontroller is able to support such high bit rates. Sometimes not the transceiver is limiting the maximum bit rate. Sometimes the microcontroller implementation is limiting the maximum possible bit rate which can be used. And what you have here is an example. If you use a CAN XL IP, you can configure classical CAN, CAN-FD, in future also the new CAN-FD variant, CAN-FD Lite, and you can configure a CAN XL protocol. So now if you have a CAN SiC XL transceiver used and put on the microcontroller with the CAN XL IP inside, then you have to do nothing. So there is not a reason to change any mode. If the IP is configured to transmit CAN classical CAN or CAN-FD protocol, then automatically transceiver is only in CAN SiC mode. So that's what I said before. If you're using CAN XL protocol, then the microcontroller, so the CAN protocol handler, controls the modes in the transceiver via this via TXT NPN, using PWM symbols to switch the transceiver into fast mode. So the transceiver is absolutely controlled by the microcontroller. You have to do nothing. You have only to configure the CAN XL IP correctly, and then it's working automatically. And here also an overview. Protocol variants here, protocol variants here on the left-hand side, transceiver variants here on this side, and you see here which bit rates can be achieved in combination with the protocol. So, and this is really absolute flexibility what we have here given, that you have a lot of combination possibilities for you and your network, and also with SiC. So you can really use CAN-FD protocol with a CAN SiC XL transceiver, and later on you can use the same ECU configured as CAN XL. So you have only to change this configuration, means the software has to be updated, and then the ECU, the hardware, don't need any kind of change. You can use the same hardware, and you can put it into CAN-FD networks or CAN XL networks. You have a lot of flexibility and a lot of freedom here with the solution we have developed for you. So then we are coming to the plug fest also Arthur has shown some results before. I will go in a little bit more detail. So here at the beginning, we have taken a look on a daisy chain topology. The reason was that we compared our solution now with the 10^1s solution. We have different distances between the ECU, and we have also a long distance between ECU 6 and 7, and then a short one to the terminated ECU at the end of the wire. And now you see some results. So here at first, this is the results here of ECU 7. ECU 7 is transmitting, and now here you see the waveform on the bus of ECU 7. And what you see here is the transition from SiC to fast. So SiC is really relaxed in all combination. So the arbitration phase is not a challenge. The challenge is always the data phase. And here you see we have nice signals. We achieve also this ±1 volt level on the bus. You see here short pulses, only 1 bit transmitted, and then you see a long phase with another level. We call it level 1. In this case, it's really logical 1 on TXD and TXP pin. That's the reason why it's called level 0. And we have really checked everything. Level 1, level 0 phase, and then short bits of one level and longer bits on the other ones. And so it's really a nice pattern to analyze wave network. So you see in the same network that we have different results. So here also ECU 7 was transmitting, but now we have taken a look on ECU 3. And sorry, here ECU 3 is transmitting, and we have taken a look on ECU 7. And you see that this impact the waveforms. So we cannot achieve with these test chips. They're not productive chips, they're only test chips, but we have here analyzed. We will not achieve the maximum level, but here you see the 0 volt line, and so we are alternating around this. So although this is fine for such kind of network, the asymmetry was really small, and also here in this combination 20 megabit could be supported. And then at the end we have also here the information about this both nodes. ECU 8 was transmitting, ECU 7 was a node where we observed here the levels. You see here also a perfect match of the waveforms. It's not unusual that we will not achieve this very short bits. So here we have only less than 50 nanosecond time that we will not achieve here the max level. But due to the fact that we have really the thresholds at 0 volt, this is fine and robust for the communication. And we said, okay, this network passed our 20 megabit test. Then we have taken a look on a network which is closer to that what we have in CAN, this linear topology with stubs. We analyzed here different lengths and different combination of lengths for the stubs. You see here 0.4 meter and 1.8 meter, different combination. And also here we are taking a look on this. Here is node 3 transmitting, and we are looking on node 4. You see here also the same behavior due to the stubs. And we have here really the problem that we will not achieve here always 1 volt, but due to the receiver thresholds of 0 volt, here also the communication is robust. It's 20 megabit. We have also analyzed 16 megabit. So then you see the impact. If the bit time is a little bit longer, then also the levels are higher, makes the communication more reliable. So it's at the end, your decision is 20 megabit here with this max level of 500 millivolt for in case of short bits. If this is a little bit critical from your point of view, or is it fine for you? Otherwise, and this is also an advantage of CAN XL and CAN in general, you can reduce the bit rate to improve the reliability of your network. And at the end, we have taken also look on 14 megabits. So you see now that's really perfect. This is really nice and is absolutely reliable. But our decision was also that with this topology, 20 megabit can be used in this network. And then we have a little bit zoomed in. You see here what's in, what is really the topic. If we have 20 megabit, so it's a little bit alternating. It don't looks like in the university in your lesson what you prefer of the kind of communication, but due to the fact that we are symmetric to 0 volt, although this is fine. Then we are coming to a more typical CAN networked topology with this single star topology. We have different wires up to 8 meter long. Here you see the terminated nodes. And with this topology, it was not possible to support 20 megabit. So then the ringing was too high. And what you see here also with 8 megabit, so you see here some dips. But here now you see the performance of the receiver. Here you see the yellow, the dips, what we have observed above 0 volt, but the receiver filtered out this noise. So you have a reliable waveform on RxD. The bus itself looks crazy, but due to the perfect filter mechanism of the receiver, the RxD signal is really nice, and the CAN XL protocol handler can receive and detect and these bits perfectly. So that was the reason why we said, okay, this is fine. And here also with this topology, we can recommend to use it at 8 megabit. Also here, another example, if phases are longer, you see here this ringing. The ringing is sometimes a little bit longer than a bit time, but the receiver really filter out this noise, and you have an excellent RxD signal what can be really decoded by the CAN XL controller. So, and my conclusion at the end, and at first, so CAN XL is really able to be used in cars. From our point of view, from the working groups, it's really fine, and it's really also a big advantage that the CAN XL transceiver supports different CAN protocols and vice versa. And from the protocol, I hope you heard that also a special variant is available, which is called CAN-FD Lite, which is a variant of CAN FD and makes some communication a little bit easier. And the CAN SiC XL transceiver combines now CAN SiC transceiver and CAN SiC XL transceiver in one network. So if you are using CAN FD node only, then transceiver is working like a CAN SiC transceiver. And if you have CAN XL protocol configured, then this is working also. So, and you have at the end also the portability, like Arthur explained before, to combine all protocol and all transceiver variant in one network. So from my point of view also, use CAN XL. It's ready and it's already standardized in the ISO specification 11898-1 and -2. And for your support, CiA offers also a lot of guidelines. We have some system design recommendation and in preparation at the moment. I hope we can release this device, this specification soon. Then if you need more information about this PWM coding, we have prepared here also an additional document. It's called CiA 612-2. Here you get a lot of information and more detailed information how this PWM coding works. And also in preparation, and I hope also that we can release it soon, is the CiA document 612-3, which explain here which option you have in CAN SiC and CAN SiC XL transceiver in the arbitration phase. That's all from my side. Thank you.
Thank you very much for your wonderful presentation. Thank you so much, Mr. Magnus. So now we only have we finally have time to do some more Q&A session, and I will do a brief summary for your presentation, and it's the Q&A session. So 感谢Mr. Magnus 的分享，他提出的 10XL 是对目前非常成熟的 10FD 协议的改进。为了在 10XL 网络中实现更高的比特率，必须改变物理层，将比特率提高到160兆赫兹。并改进 10SIG 收发器以及 10协议和 10收发器不同变体的可能组合。那么我们也看到，在刚刚的演讲过程中，有很多观众有提问。那么我们现在随机抽取几个问题，请讲师为我们解答。那么第一个问题的话，就是这个同时应用于 CAN、10FD、10SIG 还有 10SIG-XL 的收发器能否发送 10XL 的报文？数据段的最高比特率只有8兆。那么单独用高速传输模式的 10XL 才支持20兆吗？So Mr. Magnus, our first question is, the transceivers used simultaneously for CAN Classic, CAN FD, CAN SIG, and the CAN XL can transmit the CAN XL frames, but the maximum bit rate for the data phase is only 8 megabits per second. That's the 20 megabits per second speed.
The maximum. Yeah, the transceiver limits the maximum bit rate in the data phase. If you're using a classical CAN transceiver, only 1 megabit are possible. If you're using a typical CAN FD transceiver, only 2 megabit are possible. If you're using CAN SIG, typically 5 megabit are possible. So here the transceiver now limits really the maximum possible bit rate in the data phase.
Yeah. So different protocol have so different transceiver depends on their different chance bit, right?
Correct. Yeah.
好的。
And really, what also I see in the chat the question, as Arthur pointed out, at the moment all transceiver have the same pinning, independent if this is a classical CAN FD, CAN SIG, or CAN SIG XL transceiver. So you can also replace it on your board, and you have not to relay out your board. There's also a big advantage here of our solution that the pinning is the same. Also, most of the time the PDSO package or now the thinner package, which is called TSON or HSON 8 is available. So you have all kind of transceiver in the same package, in the same type of package, so that here also replacement very fast as possible. Yeah. And so I have also seen in the chat another question which is called, what's about the wire? The requirements for the wire are that the impedance is in a range of 100 ohm of this wire, if possible with a tolerance of plus minus 5% over production and temperature. So this is a recommendation for CAN FD with bit rates 2 megabit, 5 megabit, and it's the same recommendation we have for CAN XL with 20 megabit. And more or less it's the same kind of wire what you can use for 2, 5, 8, 20 megabit and as well as for 10^1, as for example. Here the requirements are more or less the same. Yeah.
Okay, thank you so much. 那我们的第二个问题的话，就是在 ECU 的硬件场景中，如果想搭建一个 CAN FD 还有 CAN XL 的混合网络，有推荐的节点数量或者说其他的更具体的信息吗？So Mr. Magnus, our second question is in the ECU hardware scenario. If you want to build a mixed network of CAN FD and CAN XL, is there a recommended number of nodes or other more specific information for the users?
Depends always on the network topology. If you are using a star topology, then the number of nodes has a higher impact on the maximum possible bit rate, like in a linear or in a daisy chain topology. So in a daisy chain topology, we have checked it in the plugfest up to 8 megabit and was not really a challenge for the transmitter and for the transceiver. You can also use more. And the only thing what you see is as longer the wire is, then you have wire effects like damping effects. So here and then also what Arthur showed before, if you go to really long wires, then the wire at the end limits the maximum possible bit rate. And here you have really to look what is the combination of wire, of stubs length, and of number of nodes to find a final solution for yourself. So recommendation we don't have at the moment. I know it's recommended to have some, but we have not worked out really a final recommendation document for you. It's a good point. We should do it, and was also now part of the Canon Automation Members Day next year that I have to work out such kind of recommendation for this member day at the end of February in Frankfurt. Yeah.
Okay, thank you so much for your answer. And due to, please.
I have seen an additional question here in the chat, but this is more for Arthur. Here's his scenario, a clear scenario for using CAN XL transmission. For example, we are using Ethernet to transmit videos, and this is also what Arthur have shown, this Ethernet tunneling. And it was also demonstrated on one CAN XL Plugfest that it is possible also to tunnel Ethernet and to show videos or to transmit video information via CAN XL using this Ethernet tunneling concept.
Okay. So thank you so much for your answers. And due to the time constraints, so please forgive me to conclude this session. And thank you so much, Mr. Magnus.
You're welcome. Thank you very much for joining this presentation.
Okay, so we're the next speaker. Please get ready, and I will do some brief introduction. Then I will signal you to start your speech. 那么下一场演讲的话是由恩智浦的产品营销经理Mike Van Heller展示呈现。目前汽车正朝着向智能化和电气化的方向快速演进，这也带来了车载网络架构的变迁。为了更好的应对汽车行业的诸多挑战，赋能未来汽车网络，Heller 先生为我们带来了目前 CAN XL 的市场现状与规划介绍。那么有请 Heller 先生来开展他的演讲。Mr. Mike Van Heller, please, you can begin your presentation.
Thank you. First of all, a quick check. Can you hear me and can you see my screen?
Yeah, I can see your screen, but the voice is a little empty, or
maybe now it's better.
Now that's better.
Okay, good. Okay, thank you. Then let me start. So yeah, thank you for the introduction. So again, a quick introduction also from my side. I'm Mike van Hagen. I'm located in the Netherlands. I'm part of the NXP team of the product marketing team, and I'm responsible for the CAN portfolio. I'm within NXP for the last 20 years in different roles, and since about 5 years responsible for the CAN portfolio as marketing manager. Yeah, so today slightly different from the other presentations you have already seen, which are more technically focused. My presentation is more on the today's market status and yeah, the view that we have as NXP where CAN XL will end up. So I hope at least to answer the questions like what kind of use cases do we foresee in the market, and things like, okay, there's two 10 megabit technologies in the market available, 10BASE-T1S versus CAN XL. What are the benefits, the advantages, disadvantages of these technologies? Just a very high level and brief, but I think it already gives you quite a good view on what will be coming up as CAN XL next technology. Yeah, so let me swap to the next slide. So first slide is about status quo. So what is the status of today about CAN XL technology? So the achievements we have reached at this moment. CAN XL has been standardized and adopted into the ISO 11898-2 2024 standard, which has been released early this year. The ecosystem around CAN XL is currently being built. First MCUs with CAN XL controllers are close to be released into the market. And we see also all the tooling suppliers which are preparing the products to support CAN XL. So think about oscilloscopes, logic analyzers, etc., which all need to support this CAN XL protocol. What we also see is that OEMs and industry partners are currently running evaluation studies to understand CAN XL applicability and capabilities. So what are the use cases where we can use CAN XL? Where does it make sense to use CAN XL? What are the capabilities in terms of speed in a network, how complex can I build my topology, etc. And also there's a big comparison ongoing again within the available new technologies, which all cover 10 megabit. So 10BASE-T1S versus CAN XL. It's a kind of a daily question I need to answer. So when should I select which technology? Then on the challenges, of course, is CAN XL is very nice as a technology. It's being introduced, but there's still an ecosystem to be built. So as I mentioned, microcontrollers are close to being released, but currently there are no CAN XL transceivers yet released to market. So the only things we need to work with currently is test chips, and we as NXP have, of course, our LB test chip, which are mainly used to run all the evaluations, which we have also seen on the CiA Bade conference, the CAN conference, where about 80% of all these test setups were running based on the LB test chip that we as NXP have provided. We have not seen firm confirmation yet from car makers on adoption of CAN XL. So also there, we are kind of in a chicken egg situation, where of course silicon providers like NXP, we need to come up with microcontrollers, transceivers, etc. But before we do really big investments in that, we of course also need to build that really CAN XL will be used in future platforms. And currently we see this again, the evaluation studies ongoing, but there's not yet really firm confirmations that CAN XL will really be used. So if you have these kind of confirmations, also please let me know, because that will help me also to build a stronger voice to get a CAN XL transceiver released sooner. 10 megabit bandwidth has two technologies fighting for the market share, as mentioned. So we have 10BASE-T1S, we have CAN XL, and each technology has their own advantages and disadvantages over the other technology. My personal expectation is that both technologies will coexist, and even within one vehicle. So both technologies need to serve the applications at each technology key competence. So I will come back to that in a later slide, but each technology has its strength and advantage and disadvantage over the other. When we come to the next slide, I'd like to talk about the use cases. So where do we see CAN XL really being considered? So CAN XL allows to merge multiple CAN-FD networks into one big CAN XL network. So it's a consolidation of multiple branches into one. CAN XL allows for longer wire lengths. So this also supports that you have a completely distributed network topology in the vehicle with longer wire lengths. And don't only think about passenger cars, but also think about trucks and buses, which have typically very long wires. And even think about trucks with trailers behind, which can even run up to what, 50, 60, 70 meters of cable length need. CAN XL proves also to have a low latency strength for latency critical applications. So this is one of the biggest advantages of CAN XL. It's very low latency if the message that you try to send has the higher priority. CAN XL provides also the higher bandwidth, which creates bus load margin versus CAN-FD. So what we see is OEMs struggle to stay below the typical recommendation, which is below 50% of bus load. Yeah, sometimes we see now with the more complex vehicle architectures, bus loads going to 60, 70, or even higher bus load percentages. And CAN XL can there provide an additional step to reduce the bus load and create margin. Example use cases which fit all of these mentioned technology strengths are typically steering and steer-by-wire systems, which require a fast response time, low latency, requires functional safety, or think about ADAS radar systems, which also again require the higher bandwidth for the ever-increasing radar resolution. So you get more and higher resolution radar chips, and all that data needs to go over the bus to the central compute unit, for example. And yeah, CAN XL can support that first step to 10 megabit, 20 megabit. If the radar bandwidth is needed to be higher than 20 megabit, of course, you need to consider to go to 100 megabit or beyond Ethernet solutions. Also, what we see is that ADAS and radar is typically a very physically distributed system, right? So you have radar chips on the front of your car, on the back of the car, on the roof of your car, if we talk about LiDAR. So also there you need the support for the longer wire, which is again possible with CAN XL. And we expect also for radar systems, for example, to remain a domain-based solution for functional safety reasons. Yeah, what you can see here is an example what we have today, an implementation with CAN FD. So all the radar chips or the radar modules are connected through separate lines to the ADAS, to the zonal unit, and with CAN XL you can really consolidate everything in one cable harness, which is then more efficient on the cabling, more efficient on the routing, and more cost efficient. Another use case might be video streaming from camera to, for instance, the infotainment system. Think about camera mirrors, parking cameras, medium to high bandwidth pictures, but not full HD resolution required, right? So if you have really the in-screen IV or in-car IVI with the full HD movies streaming to the back seats to keep your children silent on the back seat while driving, of course that needs more bandwidth. But for these, let's say, medium to high bandwidth cameras, you can really use CAN XL. And it also requires the long distance wires, for example, the truck trailer reverse camera, which is all the way back on the truck trailer. It might even go up to 70 meters. And this really requires a solution, something like CAN XL. Then, of course, software updates. Software updates also require high as possible bandwidth versus lowest possible cost. So if you want to do over-the-air updates, you want to run that data stream as fast as possible. And CAN XL can run the software updates at full speed, up to 20 megabit per second. And this is significantly reducing the software download times versus today's classical CAN or CAN FD solutions. And of course, we can also use CAN XL as a redundancy to Ethernet. So think about all these zonal implementations, which everybody is talking about today. Zonal needs functional safety, or functional safety is one of the main key features or requirements which need to go into autonomous driving cars, ADAS level 3, ADAS level 4 solutions. And today we are talking about having 2 data connections, but we also are seeing requirements popping up like differentiation of IVM technologies. So that means if you have 2 Ethernet connections and something goes wrong in the Ethernet in general, then whatever redundancy you have will always fail. So you can also differentiate by having one Ethernet connection and one CAN XL connection. And then if something goes wrong on the Ethernet side, always the CAN can still take over as a completely different protocol running on the side. So this really supports also the technology diversification, as we know, as we call that. Yeah, and then the advantages for the OEMs. So what are now really the advantages of CAN XL over other alternative technologies which are more or less in the same range of bandwidth? So we talk about time-based T1S, we talk about CAN FD, we talk about FlexRay. So CAN XL allows for real star and stub node topologies, and this is different from all the other protocols. So CAN XL allows also usable stub lengths So really going up to many meters instead of, for example, 10⁻⁴S, which only allows 10 centimeters for the stub limit, for the stub length. So that means 10 centimeters is already consumed by the PCB area itself. CAN XL also allows for easy low, mid, and high-end platform scaling. And platform scaling is very important for the OEM as soon as you have a low-end, mid-end, high-end range in your portfolio. So you have a very low-end car which has very few features, maybe only 3-4 star nodes are really required, while in a high-end, maybe you have 15 star connections that you want to make. With CAN XL, this is possible, still within the same cable harness. So you just simply add or remove stubs from the cable start points. For an Ethernet solution, for comparison, you really need to change your switch layout. You need to change your cable harness because for 10⁻⁴S, for example, you need to have a daisy chain kind of solution. And the daisy chain network, cable network, really changes from every low-end to mid-end to high-end platform, all the features that you want to add or remove. So that's more difficult for Ethernet and more acceptable and more easy for CAN XL implementations. And another big advantage of CAN XL, and you heard it already in the previous presentations also, CAN XL is flexible. And CAN XL allows also for bitrate scaling. So when you have a very complex topology and you try to get the highest bandwidth possible, this highest bandwidth is not always 10 megabits, it's not always 20 megabits. You can scale it. So if you have a more complex topology, you can scale down the data rate that you try to drive, and then you can still support all these complex topologies. Another advantage for OEMs is, of course, cost down. CAN XL supports a higher bandwidth, which might remove the requirement for physically splitting between, for example, a real-time bus and a data bus. So we have seen this as example in some of the OEM architectures with CAN-FD or with FlexRay. You have a real-time communication bus, you have a data bus. And this, of course, creates double cabling, double the number of connectors, double the amount of assembly parts in the car. So by using now CAN XL, you increase the bandwidth, you can run real-time and data communication, normal data communication, really over the same bus. And that removes the need for double data buses, removes about 50% of the cables and assembly parts and inline connectors in your vehicle. So significantly reduces the cost of implementation. And also CAN XL offers more margin to CAN technology limitations. So it's allowing for less R&D effort. So what we see today, if an OEM wants to integrate a new architecture, they need to do physical analysis, they need to do bench analysis, they need to do simulations, really to know that the data communication will always work and there will never be failing communication, which is very important also today for all the functional safety requirements. And with CAN XL, the implementation effort and the simulation effort and the validation effort becomes really a lot less because it has so much margin and typically it always works at 20 megabit. This is also what Volkswagen has shown on the ICC back in Baden-Baden, that CAN XL at 20 megabit, it really works. It really works. And yeah, this is of course the biggest mega trend we see currently in the industry: cost down. Everything is about cost down. Manufacturability. CAN XL supports direct inline flashing, and this is another big advantage. So a CAN XL bus topology you can build in your vehicle. You can directly connect an ECU to your bus. To your bus line and directly start to flash the ECU. And when it fails, you directly take it out while in the assembly line and replace it with a new one. You flash it again, you run diagnostics. If everything is okay, the car continues to the next stage of car assembly. Compare this to a daisy chain network, for instance, 10⁻⁴S or any other technology, I would say. Also, FlexRay has the same. A daisy chain network first needs to be completely built before you can really run these flashing, ECU flashing activities, before you can run diagnostics. So you first need to assemble the whole car, then check if everything is okay. If something is wrong, you need to deassemble the car, take it apart again, change the failing ECU, flash it again, run diagnostics again, and hopefully then it works. But there's a lot of overhead costs also for the OEM. So this can be prevented by using CAN XL. And also, yeah, as mentioned, manufacturability also comes back in the assembly parts. So as mentioned already in the cost down part, we can really reduce the number of assembly parts, and that's manual labor to install this wire harness into vehicles. Typically, again, I would say. So also, if you have less assembly parts, it's a less expensive manual labor activity to install this whole CAN harness. Yeah, then about the ecosystem. So as mentioned already, soon MCUs will become available with CAN XL support. Still no transceivers are released to the market. So this is a lag in the ecosystem. But what we can already today consider is a stepwise approach moving towards CAN XL. And which is the 4 steps which I put down here is really coming from a CAN FD solution, which is currently today 5 megabit maximum, but typically 2 megabit per second with a payload of 64 bytes. The next step is, of course, to move to CAN SIC. Then you can run up to 8 megabit, but typically 5 megabit and more complex topologies, again using 64 byte. And the closest alternative solution here is a 10BASE-T1S or FlexRay technology. As a third step, and this is where CAN XL comes into play, you can use a CAN XL controller or microcontroller which carries already a CAN XL controller in combination with a CAN SIC device, CAN signal improvement. This can run up to 8 megabit per second, but you have a big advantage already by using the 2048 bytes payload. And if we look at efficiency, the biggest efficiency we gain in increasing the payload size, because the payload at a certain moment, just increasing the data rate doesn't pay off that much anymore. Again, the closest technology here is 10BASE-T1S, or an alternative if you need to go to 20 megabit, then we talk, of course, about 100BASE-T1S, because 10BASE-T1S simply cannot support anything above 10 megabit per second. As a last step in this whole process, we can use a CAN XL controller and use the CAN XL transceiver, CAN SIC XL. So then at this moment in time, you can really run it at 20 megabit per second with the new voltage scheme, as already mentioned by Magnus, and you use the big payload. The closest alternative here is again 100BASE-T1S or 10BASE-T1S if you talk about 10 megabit per second. So today's fastest way for CAN XL enablement is CAN XL controller with a CAN SIC transceiver. The bandwidth gap between 8 megabit and 10 megabit might be acceptably small. And what we see today also is that the CAN SIC topology support, of course, SIC already supports longer length and more complex topologies. We expect it still to be sufficient for today's architectures, at least the majority of it. Now, if we look at the availability of CAN SIC transceivers, we as NXP already have CAN SIC devices released several years into the market, TJ 1462, 1463, and we are very close to release also our sleep mode with partial networking device, which is called the TJ 1465 and TJ 1466. And one thing I also like to introduce here is the CAN XL passive functionality. So our next generation partial networking device also comes with CAN XL passive, which actually means it's quite similar to what we had in the CAN FD partial networking device, where we have a CAN FD passive communication or a function implemented. As soon as we have a CAN FD controller connected to our CAN SIC device, and there's communication running over the network, which is talking CAN XL language, we will stay into sleep mode until this whole CAN XL frame has been finalized, and we wait until the bus is idle again. Now, CAN XL passive, of course, very simple if you talk about the old voltage scheme, 0 to 5 volts. But it becomes more complex if you talk about the new voltage scheme, because the -1 to +1 volt voltage scheme can also be received by a old-fashioned CAN FD transceiver as a idle on the bus, because it cannot recognize any edges anymore on the network. So for this, we also introduced our out-of-bound comparator, which can detect those -1 to +1 volt edges. So even at the fast phase, this one can interoperate with CAN XL transmission on the line and still remain in sleep mode without sending any errors to the bus. So this is really a solution you might consider in case you want to mix CAN FD and CAN XL communication on one CAN bus. If we talk about the CAN XL transceivers, so currently we have an L-by concept silicon. This is a proof of concept chip. It's in always active state, so there's no low power mode here. It's a 14-pin device with a lot of test pins, and this is a proof of concept which is available for sampling. And it comes together with an FPGA board from CNS, which is running the Bosch CAN XL protocol decoder. It's proven already with a performance up to 20 megabit per second. It's already meeting the IEC 62228-5 class 4 new 9 decibel limits at 10 megabit per second. And yeah, we see real CAN XL communication at 10 megabit possible, also using the ACT 1210R choke. So this is really a proven solution in the market. And as mentioned, this is the concept silicon which is mainly used today to validate CAN XL technology in the industry. Yeah, then on the MCU side, as also shown by Mr. Mutter from Bosch, there's an ecosystem on MCUs also being built up. So not only NXP is introducing microcontrollers with CAN XL ports, also ST, Infineon, and Renesas are introducing their microcontrollers. And as you can see here, it's mainly about motion control, zonal and domain control, central compute. So really the applications which require typically higher bandwidth. Yeah, then a quick comparison of 10^1S versus CAN XL. So just CAN XL, it's a proven technology. CAN is a proven technology, and it's easy and low risk to upgrade existing CAN FD and SIG networks. Complex topologies are possible, and lower latency for critical communication. Versus 10^1S, which is enabling maybe the cloud to edge connectivity on a single protocol. So there's just a need for one IP stack software protocol development. And it can reuse available software ecosystem, which is already available for Ethernet in general. On the network side, CAN XL doesn't have a node count limitation. It can support complex topologies, for example, star connections, but it doesn't have PUDL support, power over data line. Versus 10^1S, which is limited to daisy chain networks up to 8 nodes and a maximum of 25-meter cable length. But it does, on the other side, support PUDL, so power over data line. On the response time latency, general latency depends on the bus load. With CAN XL, it's scalable data rate up to 20 megabit per second. The arbitration provides priority-based event-triggered transmission, leading to lower latency for higher priority messages. So if you are very latency dependent or sensitive, you can use a very high, or let's say low number identifier. So the lower the number, the higher the priority on the bus. And with that, you have a very short latency on the bus. Versus 10^1S, where the latency depends typically on the bus load. It's fixed to 10 megabit data rate. physical layer collision avoidance or PLCA based on defined order of transmissions without prioritization. But there's a possibility, of course, to build in or implement a quality of service function, which can also add some priority-based arbitration. On the system cost, we expect a lower system cost for CAN XL and slightly higher for 10BASE-T1S because there's a need for a 25 megahertz oscillator to support the 10BASE-T1S communication. So this is more costly. This is typically a crystal which you need to put on the board. On the security side, currently CAN doesn't have a unified security protocol, but you heard already MACsec is under development at CIA. So this is maybe something that can cover this box versus 10BASE-T1S, where we have already MACsec fully standardized and implemented. On the safety side, robustness, typically CAN XL has a higher EMI robustness, and we have more margin for topology reflections, EMC events, ground shifts, etc. Due to we have 2 volts peak-to-peak margin, where Ethernet on the other side only has 1 volt peak-peak. So the higher the bus wire frequency could make these ECU emissions more challenging to manage. That's what we say. So typically CAN XL is a bit more robust against external factors. When we look at the bill of material comparison, so typically using CAN XL versus 10BASE-T1S, I would say in general, there's not a big difference. However, as mentioned, we need to have this very accurate oscillator, 25 megahertz for 10BASE-T1S, which is quite costly. The common mode choke is more expensive because it's an optimized 10BASE-T1S 240 microhenry common mode choke requirement. There's a few more components externally. On the software side, I would say there's from an upgrade from CAN-FD to CAN XL, not much required on the CAN side, but you need to build a new software stack for 10BASE-T1S. On the analog front-end side, so the transceiver itself, I would say these are cost comparable to each other. And also on the protocol controller, I would say CAN XL versus 10BASE-T1S, there's not a big difference between both of them. So this is my last slide, when to think about which technology. And I would mainly say, when you're managing smaller daisy chain networks with 10BASE-T1S, you can maximize the potential of multiple branches, decreasing the total complexity by integrating to the Ethernet backbone. So this can be a big advantage, only speaking in Ethernet over your network. When you have a clear separation between legacy functionality and new functions, so if you have an integration of a new function in your vehicle and you anyway need to develop everything from scratch, then you could consider 10BASE-T1S. Well, if you want to replace an existing function in your car, then you should really consider CAN XL because it's simply more easy, more cost efficient, more straightforward to use CAN XL. And when a high number of legacy nodes continue to be used with CAN-FD, then also CAN XL can support because we offer more bandwidth. CAN XL offers more flexibility on the network and more complex topologies. So the conclusion is there's no single solution or prescribed technology, and every architecture requires its own consideration for hardware, software, cabling, and cost. And we leave in the end the decision to the OEMs what technology to handle. Personally, I'm a CAN guy, so I prefer CAN XL, of course, because I do see the technical advantages, but I cannot see the complete picture at an OEM where they also need to set up software teams to develop software stacks, etc. Between a central architecture, which is always using Ethernet, and the edge nodes, which might use Ethernet as well, or CAN XL. So that's the end of my presentation.
Thank you so much for your wonderful presentation, Mike. So I think we have saved some time for one question, I think, and one of our audience have a question like, could you share some real application scenarios for CAN XL and its market prospects as a MCU manufacturer? What risks are associated with introducing CAN XL at this stage?
Yeah, so real use cases I mentioned already. So we see already considerations for ADAS related, steer-by-wire related applications. So typically the applications which require the higher bandwidth, lower latency, fast response, there we see really applications. I think also at Bosch we have seen already some IP tunneling applications where there might be a need for more flexible wire harness implementations using CAN XL, but then do the IP tunneling of Ethernet frames over the CAN XL transmission lines and transceivers typically. Those applications we also expect to really go into vehicles in the future. As an MCU supplier, I would say the CAN XL protocol decoders are quite well developed and in the far stage, close for release. I don't expect there's a big threat or a big risk of implementing these into MCUs today. And of course, also we need to comply to all the standards and guidelines which are available in the market. Coming from CIA, coming from the ISO, coming from SAE, whatever. So everything will be very intensely checked that we meet standards and that we are EMC compliant, ESD compliant, etc. So I would rate the risk of introduction of CAN XL peripherals very low.
Okay, thank you so much. 感谢这个 Mr. Mike 的回答。他是认为，如果在应用上的话，其实当然不管是博士还是在他的PPT 里面都已经展示了很多，包括这个 ADAS 还有毫米波雷达。然后他自己本身呢是认为，现在将 CAN XL 引入并不会带来一个非常大的风险，他自己是比较乐观的。那么接下来的话就是我们迎来了今天的最后一位演讲嘉宾，也就是来自于宏科智能互联的技术主管陈浩先生。目前呢 ，CAN XL 的发展和推动源自于近些年汽车电子的迅猛发展和技术激增，然后与 10base T1 的底态网之间的差距也是比较热门的话题。陈浩先生将从物理层的角度为我们阐释二者之间的差别，并比较这两种协议的应用与实际问题的处理。那么我们欢迎陈浩先生开始他的演讲。成功，你没有开麦。
不好意思，现在可以听到吗？
好，可以听到。
对。各位朋友们，大家好，欢迎来到2024CAN XL 国际研讨会的直播现场。我是宏科智能互联的技术主管陈浩。今天想跟大家分享的主题是CAN XL 和以太网之间的应用和对比。当然，这里提到的就是作为CAN XL 的对比技术，以太网主要是指10兆下的10base T1S。那本次的分享呢，主要分为4部分内容。前2部分先简单介绍一下CAN XL 和车载以太网。第3部分是本次想分享的重点，是关于CAN XL 与车载以太网的对比。我会从一些关键的参数，包括技术应用上，然后以及成本等多方面进行两种协议的一个具体的对比。那第4部分是关于CAN XL 与车载以太网之间的，就是现在的一些具体的应用。那第1部分是CAN XL。CAN XL 作为CAN网络的那个第3代协议，它在数据上是在那个总线的波特率上是可以高达20兆，然后并且是可以向下兼容CAN CC 和CAN FD。与CAN FD 混合的话，相当于是整个网络有CAN FD和CAN XL。这样的那个网络波特率可以达到8兆每秒。那对于刚才其实我看直播中很多朋友也有提到的一些问题，就是说对于CAN XL和CAN FD这种网络混合的情况下，那CAN FD是如何处理这个CAN XL 呢？那其实一个简单理解就是说，CAN FD会对CAN XL 的报文做到一个自动忽视，其实它是将CAN XL其中的一个字段。然后给到CAN FD一个提示，然后将CAN FD这边的网络就是直接自动忽视掉这个CAN XL 的报文。 那也就是说，在CAN XL 网络下，它可以同时拿到这个CAN XL 和CAN FD 两种通讯协议的报文。当然，这里提到的是最高8兆的波特率。那对于CAN XL 的一个主要特点呢，它仲裁域还是像传统的就是经典的CAN CC，然后包括后来的CAN FD 一样，仲裁域还是最高是兼容就是CAN网络，最高达到1兆每秒的波特率。那数据域它是最高可以达到20兆每秒，然后具体的那个数据段它可以达到2048个字节。那对于这个CAN XL 的一些更新的点，就是相比于之前的CAN CC 和CAN FD 来说，它增加了虚拟的CAN网络以及更好的寻址操作。这里提到更好的寻址操作是在字段中有那个 AF 这一位的具体体现，它不仅是向内的，就是CAN和CAN FD 网络之间的一个寻址，还是有向外的这种和以太网报文之间交互一个作用。那这点具体也会在后面进行一个解答。然后另外一个点就是说，CAN XL 相比于之前的CAN CC 和CAN FD，它在数据量上有了一个本质的一个提升，有一个非常大的一个提升。那它为了保证这个数据的准确性，它提到一个双 CLC 校验的一个机制，这也是CAN XL 的一个新的特点。那整体来说，CAN XL 还是作为100兆的以太网和CAN FD 之间的一个补充。它是对标这种10兆车载以太网的一个总线协议。那相比于这个CAN FD 之间，CAN FD 的一个数据波特率，它最高是5兆。那么在无论是国内还是国外用到这个CAN FD 网络，它一般会在500K 2兆，也就是数据波特率会在2兆作为一个典型值来使用。那对于CAN XL 来讲，它数据波特率最高可以达到这个20兆。它同时可以涵盖2048个字节，这是刚才提到的。那对于这种数据的一个特点，它除了一个功能强大之外，还可以兼容这个以太网报文，同时放在这个 XL 帧里边进行一个数据的直接交互。另外一个点就是说，它这样理解是非常简单的，每个字段都有多种的这个采样点，然后并且是向内兼容，就是完全和之前的CAN CC 和CAN FD 是完全兼容。然后另外一个点就是说，在CAN XL 协议下，它不再回读这个发送的信号，会把这个整体的通讯效率会提高。然后再一个点就是安全性方面会有双 CRC 作为一个增强性的校验。不好意思，这一页 PPT 是展示了整个CAN XL 一整帧的那个数据帧的所有字段。我们可以看到它包含内容是非常非常多的，特别是在前面仲裁段还好，特别是在第2段的那个控制域这里，它是相比于之前的CAN FD 网络是增加了特别多的一些字段。那ADS 这里它其实是主要是控制这个数据波特率的传输，就是作为一个 fast 模式的就是高速传输。那另外需要关注的是在后面一个就是 IDE 这方面，就是它的就是CAN XL 的 IDE， 它实际上是只有11位的IDE， 它没有那种扩展帧的形式。然后在控制域这段，有一个比较关键的字段就是 SDT， 这是一个CAN XL 整个字段中应该是最关键的一个字段。它这个字段它相当于是解释了为什么CAN XL 网络是可以向下兼容CAN CC 和CAN FD， 以及向外兼容那个以太网的一整帧报文。它相当于是SDT， 它是服务数据单元的一个类型，它可以通过修改 SDT 这个字段的值来确定我现在携带的报文的类型是就是究竟是和总线上哪些节点要做通讯的。它比如说我可以将 SDT 设定为一定值之后，和总线上的CAN和CAN FD 节点做映射，然后也可以将 SDT 设定一定值之后和外部的以太网帧之间做映射。那 SDT 的不同的设置也对应了后面的包括VCID 以及包括 AF。就是假如说这里 SDT 是作为一个和以太网帧的一个映射，那后面的 VCID 和 AF 中，它也对应了一些以太网报文中的一些，比如说虚拟网络呀，然后以及一些目的地址的一些映射关系。然后另外一个点就是2个 CRC，PCRC 和 FCRC。PCRC 是相当于是在数据段之前，然后基本上是控制域的最后来作为一个 CRC 校验。那这里 作为一个 PCRC 的校验，是为了让前面这些复杂的仲裁和控制域之间控制域这两部分的一个内容做一个准确性的校验，特别是对 SDT 这个字段作为一个准确性的验证。那后面在2048个字节传输完毕之后会有一个 FSRC 的校验。那这里不仅仅是对这个传输的数据域这一段进行一个校验，那另外还要对前面的这个PCRC 也会参与这个校验。那刚才提到的 SDT 字段是看 XL 里面比较关键的一个字段。那假如说我们要和以太网进行传输的话，那 SDT 在这里就是会把它置为一个那个 SDT 置为5。那将 SDT 这个值置为5之后，它相当于就可以映射一个完整的以太网报文。就比如这里提到的，如果是一帧符合 IEEE 802.3的以太网的MAC帧，它我们在传输这帧以太网的时候，其实主要关注的几个点就是说，我以太网这帧报文的原地址和目的地址，以及我具体的 payload。然后如果有的话，还会涉及到那个 VLAN ID 的一个标记。那对于将看 XL 中 SDT 置为5之后，它是如何把这个整个以太网报文映射到看 XL 这帧报文里的呢？那首先，目的地址它就会放在这个 AF 里，然后 payload 就会放在整个的数据段里。那具体的这个 VLAN ID 标记会放在这个看 XL 报文里边的这个 VCID 里，然后以此来形成一整帧的那个看 XL 和以太网 MAC 帧之间的一个映射关系。这里就是提到的，它有一些具体的目的地址会被标记在这个看 XL 的报文帧里。那这样的一个好处就是说，我们之后的一些通讯就可以像以太网这边是面向 SOM， 就是面向服务的一个通讯方式。然后另外一个点就是我们在实际使用的工程师来说，我们实际使用上可以一根线缆就可以包含线下兼容FD， 然后我本身的看 XL， 当然我可以对外去兼容这个以太网的报文。那整体的成本是要相比于其他用协议转换的网关也好，用其他的一些拓扑来处理也好，是极大的能降低这个成本的。这个是一个看 XL 相关的一个特点。那另外一个点是车载以太网。那车载以太网的它是它诞生的一个原因就是说，为了解决传统的这种总线之间的一个带宽，主要是带宽和延迟的一个问题，然后满足现在的汽车电子整个系统下一个复杂的一个高带宽的一个需求。那特别是现在自动驾驶相关的，然后一些自动驾驶的传感器，包括一些信息娱乐系统，然后其实现在在以太网上都有了很广泛的一个应用。那以太网的一个特点呢，它相对于传统的总线来说，它的传输带宽是有一个极大的提高。那整体的线内就是相比于那种传统以太网来说，车内的就用这种车载以太网协议，它的一个布线复杂度和线束重量是大大降低了。然后它并且也是支持就是很多以太网方面的一些上层协议，包括一些它的总线拓扑。那具体来说，对于看 XL 和以太网之间的对比，我们分别从1、2层功能，然后包括我后面有提到这个应用相关的一些属性，然后包括一些具体的对比。那先看1、2层的一个功能，在1、2层功能上，首先是数据的字段，以太网这边是因为以太网的报文它有一些必要的就是本身的字段，它可能是最小从46个字节到最大1500个字节的一个数据。那在看 XL 里边，它其实数据段是可以从1到2048个字节是随意选择的。那另外一个点就是真的优先级是看 XL 这里留了11位，就是11位的一个看 ID 作为那个优先级的一个标识，然后在Space T1S 里面是802.1Q 头部的这个 PCP， 它留的是3位的一个这个真优先级一个标识。那总线方式就是一个是走这种仲裁机制，一个是走这种轮旋机制的。那仲裁机制其实也是整个看网络的一个显著的特点。那它就方便了我们在整个总线通讯中起到一个良好的一个就是访问形式吧。那另外一个点就是说，在物理层这边，它对于总线的开销， 看 XL 相对于10兆的以太网来说是有非常显著的一个优势的。我们在就是看 XL 的数据段上来说，它可能隔一段数据它会有一个位的填充，那加上这种填充之后，它其实总线的开销会额外多出9%。那相对于以太网这边，它用这种 DME 的机制，它整体的总线开销可能会达到20%。那相比之下，其实是差了近1倍的一个额外的总线开销。那这样也就在一定程度上是说明，看 XL 相对于车载以太网来说，就是主要是10 base T1S 的这个车载以太网来说，它这个总线开销包括整体的效率是要比车载以太网来说要更高的。那整体的另外一个点就是在安全性的校验上，在 CRC 校验上，那整体的性能是要优于这个 X3 包括以太网的。另外一个点就是说，看 XL 相比于10兆的车载以太网，在具体的应用上，传统的车辆架构还是以CAN和CANFD 为主，特别是在动力系统上。那我如果想要提升更高的数据带宽和总线的传输速率的话，那我假如说面临CAN XL和10兆的以太网来让我选择，那我会考虑到，比如说这种是否能解决我遗留的一些CAN和CANFD 网络，能把它更快的给兼容掉。那这也是CAN XL 的一个特点，就是它可以向下完美的兼容这个CAN和CANFD 网络，它并且可以在就是假如说就是一辆车上它的主干通信网络还是以这种以太网为主的，它可能是100兆或者1000兆，当然我可以通过CAN XL 的网络来和这种以太网报文之间作为直接的交互，并不需要额外的这种特别多的这种网关机制来改变我整个网络拓扑。那另外一个点就是刚才评论区中也有朋友来提问到的，就是说在于安全机制上面，我们以太网这边有一个 MACsec 的机制来作为一个安全的验证。那CAN这边它有一个 CANsec 的一个机制，但是这个机制目前还在CiA 这边正在研发中，目前并没有一个很好的开展。但是这个机制是它作为它对于CAN XL 网络来说，它并不是一个必选项，它是一个可选的，就是我们可以按照自己的需求来选择这个安全机制是否是要增加出来。然后另外一个点就是，在故障输入方面，就是CAN XL 它可以发送，就是有意的去，向总线上发送这种错误帧，去检验其他节点一个，比如说纠错能力或者说收发接收能力。当然这个点是仅仅适用于博士这边的CAN XL IP。这张图是在不同的总线负载下、不同的 payload 下，我们对CAN XL 也好，以及 X3 和10base T1S 之间的一个对比，然后我们不断提升这个数据域的数据的具体的 payload，然后来验证这个具体的总线上这个整体的一个净负载率，来比较它们之间一个效率。那可以看到，我们拿10兆这个左右来作为一个对比，那其实一开始来说，这个车载以太网在405字节之前的一个负载效率下，它整体的那个总线带宽的效率还是比较好的，但是在405字节之后，它其实是逐渐不如这个CAN XL 的一个那个净波特率的。那也就是说，假如说我们如果选择是在这种高负载、高带宽的这个环境下来选择一种通讯技术的话，它其实正常的对比来说，CAN XL 相比于10兆的车载以太网，它是有一个比较明显提升的。当然，在128字节的情况下，其实包括 X3 也好，10兆的这个车载以太网来说也好，它基本上都是相近的。那涉及到一些物理层的对比，包括一些就是收发器和收发器引脚对比。那看 XL 这边可能相对于10兆的车载以太网这边要有优势的地方要更多。第一是收发器的选择，它可以因为整个CAN XL 来说，它对于下层的CAN CC 包括 CANFD 它都是同样的一种网络机制，只是在上层协议上可能有了不同的改变。那对于这种底层的收发器，它都是可以互相切换并且互相操作的。那我们在一个CAN的节点上，它可以通过改变不同的收发器来适配不同的网络。比如说，我同样一个CAN节点可以去选择不同的高速收发器，还是说 FD， 还是 SIG 收发器，还是 SIG XL 收发器，它都是可以自由选择的。那另外一个点就是说，这里边的所有的收发器都是2个引脚。那我们在这个看的节点上，其实都只需要关注这个看高看低2根线，就可以保证这个总线的一个正常的通讯。那相比于这个10兆的车载一体网而言的话，它的收发器选择就比较局限，然后并且是在这个硬件的这个拼角的这个收发器的选择上，它的线数可能是要更多，然后成本相对来说就更高一点。再有一个比较重要的点就是在安全性上，看 XL 的所有节点它是相互独立的，因为我们前面提到整个看网络它的通讯方式都是在走一个仲裁的机制。那我总线上突然需要一个节点，还是说突然增加上一个节点，我可能会影响到这个总线的负载。但是在安全性上来说，我所有节点相互独立，它并不会出现一个明显的故障。那对于这个10兆的车载一体网来说，它是需要一个主节点来调动整个网络的，所以说它可能会存在某一个节点出现故障，来导致这个整条总线上会出现一定的问题。那对比这种价格优势来说的话，其实整个看 XL 和10兆的车载一体网，它相对于就是我从看 FD 往上再升级做到这种看 XL 和10兆的车载一体网，那这2种技术之间的一个对比，它其实是差距并不是特别大。但是相对于再底层一些，比如说整体的那个线数的一个开销，就是假如说我同时用这个看 XL 和10兆的车载一体网都跑到这个10兆一个具体的通讯，在这个总线上，那我可能看 XL 加上一些头部的那个仲裁域也好，那个控制域也好，包括尾部的一些CRS、ACK 胶原确认也好，那我整体的传输速率可能要在11兆，但是在以太网这边，它可能需要高达25兆的一个波特率才能保证总线上的传输是以10兆来进行的。那整体的额外开销相当于是一个是10%，一个是250%。那另外一个点就是，我们刚才提到的在收发器选择上，包括这个 ECU 的引脚上，那看 XL 这边在引脚和这种线数的需求上是要明显低于这个10兆的车载一体网的，所以它这部分的成本方面可能会存在一些比较大的优势。那这也是整个看 XL 和车载一体网之间在价格上的一个明显的一个优势。那最后呢，是关于这个看 XL 和车载一体网的一些具体的应用。那其实无论是看 XL 还是这个10兆的车载一体网，目前比如说国内外的一些车企，它其实就是多多少少都有涉及。可能国内这边不仅仅是10兆的车载一体网，甚至是100兆、1000兆，甚至是某一些传感器会用到一些万兆级别的车载一体网总线都是存在的。那可能像一些欧美市场，特别是欧洲这边，会在这个看 XL 上的应用会多一点，然后以及车载一体网可能也只是用到这个10兆的会多一点。那其实10兆以太网和看 XL 它们都是作为这种100兆通讯和这种看 FD 2兆、5兆、8兆左右通讯的一个补充，作为一个10兆、20兆的一个补充。那这2项技术的出现，也就是避免一个我们目前的需求情况下一个整体性能的一个浪费，就是我可能并不就是某些情况下我的总线上开销我并不需要100兆，那么我往下可能看 FD 又不太足够，但是我可以就是如今有了这2种新的技术，我可以取一个比较中间的值，用10兆、20兆左右的一个带宽来驱动于我这条现在需求的一个总线。那另外一个点就是说，特别是看 XL 的一个技术产生是缩小这个每个端口之间一个成本方面的一个性能差距，因为他们在整体的那个鲁棒性还是通讯效率上都是要比其他的那个总线方式要更就是表现要更好的。那么这张是我借鉴了一张 NXP 这边的一个对于这种网络就是网络架构的一个图。那首先这个第一张图就是我们目前的这种基于域的架构，我们可能在就是车的一个整体的就是整车的一个架构设计中，可能会比如说把 ADAS 系统放在一边，把车身放在一边，把一些那个具体的引域的系统放在一边，然后它们之间通过 它们之间就是每一个节点它都是一个域，然后通过域之间的这种通过网关的交互来实现就是多节点之间通讯。那么每个域之间我们可能会有不同的总线协议，那么我们可能在这个主干网络上会加入一些比如说车载一体网或者是一些高带宽的这种通讯协议来作为一个域和域之间的一个数据调度。那基于这种车身域的一个架构，它其实后面还有这种跨区域的一个形式的架构，然后以及包括后面这种整合型的计算的方式。那也就是说，我在整车的这个架构设计上，我不再关注于某个域，或者说我某个域之间，它的如何通讯，我是不再考虑的。那么我可能在几个域之间，然后它们之间的通讯选择上，就是它几个域之间的一个它们之间一个沟通的一个总线的铺设上，会选择一些额外的新的技术，就像这里提到的CAN XL 和实照的车载一体网。那当前架构下，刚才提到的这些域之后，它可能在明年2025年，然后以及之后的2030年之后，我们会就是对这种整车的一个架构会再做一些就是一些新的补充。那比如说，我们可能到那个2025年会把这种车身域的这种集群的方式来带入到就是当前的这个就是整车的一个架构下，然后会把这种就是个 ADAS 的自动驾驶这种辅助系统，然后和比如说车身计算机这种VCU 这种网络，然后会单独摘出来，然后向整个就是车身的这种架构来作为一个转变。那另外一个点就是到2030年之后，可能会有一个全区域平台一个新的架构，这种也就是上面提到的那种集群式的一个架构。那在这种架构下，它其实是把多个模块，然后会放在同一个那个车身计算机，然后和自动驾驶这边来进行相互连接，然后并且把这种连接和配上影音娱乐系统，然后它还是依旧存在，然后就是把这种多架构的一个核心，然后集群到一整个车身中，然后作为一个集成化。那这里是有提到一个CAN XL 的具体案例，然后这里提到的是整个车身上可能有4、5个雷达，然后向就是中央的 ADAS DC 上去不断的去更新这个数据。我可能是一些雷达，包括一些传感器，包括一些各种各样的这种，就比如说一些摄像头之类的传感器来定时的去发送一些数据。那其实这种传感器向中央的这种 ADAS 系统提供数据的形式，其实在 CAN-FD 网络架构中已经存在了。那像传统的500K 2兆的这种 CAN-FD 网络下，那么我每次传感器出来的数据比较多，那么我一次发送的数据我并不足以代表我比如说拍摄到一些视频，或者说一些距离的就是距离位置一些信号，那么我可能会通过 ISOTP 或者说多帧的形式来向这个中央去就是不断的去反馈信息。那有了CAN XL 之后呢，它相当于是我可以在高速的带宽一个通讯下，我每次是可以高达2000个字节的数据，然后向这个中央的 ADAS DC 里边去发送这个我的一些传感器的一些状态信息啊，一些捕获到的一些视频、音频啊，包括这种位置的信息。那相对于这种传感器的这种而言，那其实CAN XL会在今后的这个汽车电子市场里边会占有一定的地位。那车载一体网的主要应用，它其实车载一体网车载一体网它其实主要的一个应用场景还是会放在这个自动驾驶的领域。那对于自动驾驶领域它来说，它可能比较依赖于各种各样的传感器，比如说这种雷达、摄像头，包括激光雷达等等。它其实和之前的CAN XL 的那个案例是有一定的重合点的。但是车载一体网它相对于CAN XL 来说，它可能实照并不是它的一个比较常用的地方，它更多的是像100兆、1000兆的这种车载一体网，是车载一体网这个总线协的一个主要的那个领域吧。然后它除了这种自动驾驶的技术，包括这些传感器来说，它另外一个点就是说在信息娱乐系统方面，因为像这种多媒体的一个传输，比如说音频、视频这种，它像这种传统的现场总线来说，它完全是达不到的。那车载一体网在这方面，它可能会那个优势会更大一点。比如说传几百上千兆一个音视频的数据，它还是会效率非常高的。 那整体而言，CAN XL 和10兆以内就是10 base T1S 来说，它们相比较，它们其实都是作为这个传统的CAN KFD 网络和高速的以太网之间的一个补充，就是说我们在10兆、20兆这个领域应该选择哪种技术来适应我们当前的汽车电子下一个整车的一个架构。那对于这种CAN XL 来说，它一个显著特点就是说我20兆就是我10兆、20兆的一个波特率情况下，我到2048个字节都是没问题的。那么我向下会有更好的看网络的看网络的延伸，因为我们都是从那个看 CC 看 FD 就是一步一步发展过来的。那相比于这种车载以太网也好，包括 FX3 包括帽子的也好，它有更强的一个鲁棒性和稳定性。那它一个比较大的优势就是说，我看 SL 是可以完全兼容这个以太网的整帧豹纹的，这也是我们第一部分所提到的。那对于这个10 base T1S 来说，它是一个全新的网络架构，然后它可以向上扩大，就是有更高的一个扩展性的可能。就比如我可能我今天在这个总线的下面，我用的是10兆的车载以太网，那我可能会有一些具体传感器和具体的传感器的一个需求，包括那个整车总线那个带宽一个需求，我可以向上去扩展到百兆百兆、千兆，甚至是万兆一个车载以太网的一个总线需求。那么车载以太网它主要的一个优势是在于这个自动驾驶的新技术上，它其实像传统的这种车身控制呀、这种底盘呀、这种车身相关的，它其实并不是它的一个优势所在，它主要还是面向于这种自动驾驶的一些传感器的领域，可能会有更高的一个就是体现它优势的地方。那对比这两种总线技术来言的话，没有哪一种网络是存在绝对优势的。然后这一点刚才恩智浦的麦克也有提到，它其实我们具体来选择就是选择哪种网络是要看我们具体的应用的。那假如说我们是为了有更好的这种和传感器之间做联通，那么我可能觉得这种百兆、千兆的以太网可能会更有优势。那就10兆、20兆这个领域而言，那相对于成本来说也好，鲁棒性来说也好，整体的稳定性和传输的效率也好，那看 XL 来说，它是比较有一定的优势的。那以上是我这次想分享的主题的所有内容。那么关于我们红科在这个看 XL 上面的一个进展来说的话，我们和德国的 PIC， 然后现在有了一定的合作，就是在这个今年已经完全通过了这个 PCAN XL 的一个测试版的一个就是评估版的一个就是技术验证，它向下也是完全可以兼容这个 CAN-CC 和 CAN-FD 的，然后以及在具体的那个 CAN-S 网络那个通讯中，它也是可以做到就是完美通讯是没有问题的，并且这里的 CAN-FD 它向下兼容也可以兼容这个标准的 ISO 的 CAN-FD 以及非标的这种 non-ISO 的一个CAN-FD 的一个通讯。那整体的这个测试版是基于这个 FPGA 来实现的，然后看的通道数可以调整。我们目前做的是这种 PCIe， 然后包括这种 USB 接口的，就是都有测试过，都是没问题的。然后基于这个CAN-SL 的评估版来说，我们后面也会就是提出一系列产品，比如说像这种传统的看 XL 转 USB， 然后以及看 XL 转 PCIe 这种板卡，甚至是看 XL 和之前的看 FD 网络、看 CC 网络来做互相转换的一种网关。那对于这种标准的接口卡来说，我们目前是已经做到了完美验证，就是现在做的是这种 API 的实施和一些软件上的搭建，那会在明年会全面推出整个看 XL 系列的产品，然后硬件端是除了这种接口卡和网关之外，然后软件端会包括全新的 PCAN X Pro 7，然后会在这个7版本的 PCAN X Pro 软件里边，搭载这个看 XL 的这个整个网络通讯。那另外就是 PCAN 的一个特点就是说它的 API 是全面开放的，我们会在这个整个看 XL 网络的情况下，它也会推出这种全开放的 API， 然后并且 Windows 和 Linux 系统都是支持的，会在这个那个 Linux 下推出这个 Socket 的看 XL。那以上就是我这次想分享的全部主题。
好的，
接下来是 Q&A 环节。
好的，感谢陈浩先生的精彩分享。那么接下来的话，我们就进入最后的一个 Q&A 环节。因为考虑到这个时间因素以及刚刚大家都没有时间做一个很好的 Q&A， 所以的话，我们给每位讲师，就是今天的所有的专家嘉宾，我们都分配了2个问题做现场作答。然后呢，没有被选中的观众的问题也不用担心啊，因为针对今天研讨会中大家提出的问题，我们会专门去出一期 Q&A 的推文，来完整的解答大家的问题。So thank you, Crystal, for your excellent presentation. All right, now we are moving into the final Q&A session. Given the time constraints, we are consider the time constraint. So we are allocate 2 questions to each speaker for live answers. For those whose questions are not selected, don't worry. After today's seminar, we will be posting a Q&A article to provide comprehensive answers and all the questions are raised. So dear speakers, we have posted the selected questions for each of you in the chat. So please answer them in the order of your pronunciations. I think Crystal, you can finish your questions first, and then we will under the order of the presentation. Like the first is your question, Crystal. 所以的话，我们接下来的话会按照之前的演讲顺序来回答一下大家的问题。那么我们先把这次成功的演讲结束之后，我们把成功的这边的问题回答完了，我们再按照之前的演讲顺序来进行。
那个因其我现在 Teams 看不到小通那边。
那个你可以打开你的 Chat 聊天，在聊天里面。
哦，稍等。
So Crystal will answer his questions first, and then we will your speakers can answer your questions as under the order of the presentation previously.
Okay, I got. 第一个问题是看 XL 报文怎么包含以太网帧？那我先回到一下我的 PPT， 就是我在一开始有讲到这个具体的这一块，对。在这部分有提到 SDT 是看 XL 的一个比较关键的字段。当 SDT 置为5的时候，它其实是整个看 XL 的报文，它可以映射这个以太网报文，它就相当于把以太网报文中的原地址、目的地址，然后以及包括这个 VLAN ID， 然后以及包括具体的 payload 都加载在了这个看 XL 这个报文里边。那这样的话就可以将看 XL 报文来完全承载一帧完整的那个以太网的 MAC 帧。OK， 然后看一下第二个问题。第二个问题，电动汽车中应该如何选择看 XL 和以太网技术 ？OK， 那其实我最后也有提到，就是关于这个如何选择2种网络的话，我们一定要看这个具体的应用场景。如果是一些就是我个人而言是比较偏向于看 XL 网络来铺设整车一个架构的，那对于一些这个比如说高性能的传感器的那个通讯的总线选择的话，还是会偏向那个以太网这边多一点。但是在10兆、20兆这个领域，还是看 XL 它的整体从成本也好，从稳定性也好，还是比较有优势的。
好的，感谢陈忠这边的回答。那么接下来的话，有请我们国际的技术专家来进行我们的一个 Q&A 环节。So first, the 2 questions is for Mr. Sisme and Mr. Zedwang Ji. So would you please to answer these 2 questions for our audience?
Can you read them, please? Because unfortunately, we don't have a chat function.
Oh, okay. So you can see the chat, right?
No, you can't see the chat.
Krista, would you mind to cancel the screen, share screen? To cancel that. 就是你把那个共享屏幕先关一下。
好的，稍等。
You need to leave full screen mode, and there is a button to visualize the chat. But maybe Christo or somebody can read the question for them.
Okay, so the first question is the first question is how to evaluate the seek function of the transceiver, and thus the impedance of the seek type 50 needs to have to be tested for certification.
Did you get it?
No.
I can answer for you. I can answer for you with this. Yeah. So that's a physical layer question. So that's more or less I can answer here. Yes. The SiC impedance in the active recessive phase is standardized and will be also tested in the conformance test. So here you have really a company independent test house where test our devices independent from which vendor, and that you can really believe that all these functions are in. And you will see it also in the data sheets, like in the ISO, that especially the SiC impedance parameters are in and has to be guaranteed also by the vendors itself. And only one information for all, in the released version of the ISO 11898-2, which is the physical laser specification, there were some editorial bugs. So, for example, notations in the figures and then the tables were not the same. We are working on this to fix this, and also we are using the chance to precise some sentence and explanation. And I hope in the first part of next year, also this updated revision, which might call ISO 11898-2 revision 2025, 2025, will be released.
Okay, thank you.
And then these parameters are described exactly in this document.
Okay, so the second question is, will low-speed fault tolerance can be used for in the future? And is the ISO 11898-3 still likely to be updated? Is the second question.
For fault-tolerant CAN transceiver, please go into the museum.
Okay.
I don't know if anybody offers these devices again, but I expect from all vendors this device are under discontinuation. So fault-tolerant low-speed CAN transceiver you should not have in mind if you're discussing about CAN XL. For CAN XL, use minimum CAN FD, better CAN SiC, or the special CAN SiC XL transceiver.
Okay, thank you.
I would also agree there with Magnus. Yeah.
I can't hear. I can't hear you, Holder. I can't hear you.
Yeah, but also for your information, I don't know if the ISO standard for fault-tolerant CAN transceiver is active. It might be also that the part 3
is active,
but not updated.
But there's no recommendation to use it anymore. There are some legacy networks using it, and of course the chip makers will support that until the last of these implementations is gone. And I agree with you. Let's go and put them into the museum.
Okay. So the next part is the questions for Dr. Mutter. Dr. Mutter, could you see the messages in the chat?
Arthur, you have to unmute.
Other, I can't hear.
Very good. Yes, I can see the chat, and I just read the question so everybody can hear it. It is CAN XL addressing and arbitration separate? Question mark. What is the reason for this?
Yeah.
So we figured out during the standardization and lots of discussions going on that the CAN FD 29-bit identifier or 11-bit identifier are very cool and simple, but it's just one field, and one field means that people put a lot of different things into this field. They put the priority inside, they put the source and the destination address inside, they put some additional information in, and this field gets very complex and everybody partitions it on its own. And we said we want to be flexible because with zone architectures, things might change, and therefore we want to give one separate field for every information. So we have one field for the priority of the frame, and this is the identifier. And all other fields, this is a slow field, right? The identifier is slow because it's used for arbitration. And all the other fields are in the data phase and are sent as short bits. And these are the virtual CAN network identifier, the SDU type, and the address field. And so we can have a big flexibility because you can change the address at any time or the priority at any time or the virtual CAN network ID without breaking the whole system. And therefore, we separated all these things. But this is just an offer. If you say, I don't need this, you can go on using the identifier for everything. The second question is, it's not so easy to read. CAN bus technology is I don't know the word, there is some typo inside, but is the current CAN XL the limit of this communication technology? I think the question asks, will there be a CAN XL++ or something like that? With CAN-FD, we said CAN-FD is the end. There will never be something beyond CAN-FD. And now we have CAN XL. So I never say no, but at least from the physical layer, my feeling is, and also from the protocol, now we have everything in that the modern protocol has. Maybe we think different in 10 years, but from today's point of view, there is no intention to do something new at the moment.
Okay, it's limited for now, at least.
For now, at least, there is no idea for next generation because we have everything inside. So when new requirements come, maybe in 10 years, then maybe something changes. But at the moment, we think we have the perfect package.
Okay, thank you.
I can also add here to the statement. So the main advantage of CAN is really the star topology or the multi-node topology, how it is called. And here, really, 20 megabit is the end. We see it also with 10 megabit Ethernet. On the physical layer point of view, you have much shorter pulses, means 40 nanosecond pulses, which is equivalent with 25 megabit in CAN XL. So here is really the end of the physical layer story for such kind of bus topology. Then you have to change to point-to-point solution like a 100 megabit, but then you have really complete different scenario. And for 100 megabit and higher, you have really an existing technology available. Yeah.
Okay. So the next two questions.
This is also the next question.
Yeah.
In technical solution, I hope it means 100 megabit and not 100 gigabit. So in a car, I don't know that 100 gigabit is really under discussion. What I know is that 1 gigabit at the moment is ramping up in cars. So, but also 100 megabit is complete different technology. It's point to point. And here you have also so-called full duplex. It means both nodes can communicate at the same time. It's a complete different concept on the physical layer. And also here, no bus, only point-to-point is possible, though they have really complete different focus of a kind of a topology concept. And though you cannot compare Ethernet 100 megabit and higher Ethernet with CAN. So, and as Michael has pointed out, CAN is much cheaper than 100 megabit, for example. Here you have a big cost distance between CAN and 100 megabit by a factor of 5 to 10. Yeah.
Okay.
So, and the next question is networking test. Yes, you have seen that as longer the test is, there's more nodes you have on the bus. So then this has an impact on the waveform. And also here, the quality of the wire is very important. There was also another question, termination resistance at the end of the nodes is really in CAN XL 100 ohm. What is the reason? During the discussion with CAN XL, the OEM found out they have not a wire with 120 ohm impedance in the car. They have only 100 ohm impedance in the wiring harness, and so we changed it now to have a better matching and impedance matching in CAN XL to achieve higher bit rates. Yes, for CAN XL, 50 ohm overall termination is recommended. Mike, now you.
Okay.
Okay, shall I continue with the questions to me?
Yeah.
So the first question to me is both transmitter and receiver nodes of CAN XL need to be sent PWM codes when they cut too fast. These two codes can't be aligned. Does this have a big impact when there's a deviation? And I'm not a very much deep level technical expert, so I either like to ask Arthur or Magnus to answer this question properly.
Yeah, thanks. Yeah, all nodes or all microcontroller in a network have to send PWM symbols to the transceiver, independent if this is a transmitter or a receiver. The receiving nodes detect directly, okay, on my TXT pin, this is not a normal transmit request. This is a PWM symbol to switch my receiver thresholds from typically 700 millivolt to 0 volt. So at the beginning of this phase, you have a short spike on the bus from all receiving nodes, and then they're stopped and transmitting. They block the transmitter and receives the frame correctly. So, but this is the reason why the transition mode from SIG to fast is very long, around about 2000 nanoseconds, so that all the spikes are over and the network is stable. Yeah, and this at the end has no impact and is really explicitly specified how it should work, and so we don't expect any impact from the receiving nodes on the transmitting waveform.
Maybe I can comment on that. Absolutely correct what Magnus said. I thought the question asks if sender and receiver have PWM symbols and they are not aligned, and the good thing is only one sender exists and the receivers send PWM symbols, but they have no meaning at all, so they don't need to be aligned. So deviation between sender and receiver doesn't matter at all when we look at PWM symbols. The receiver only says to its receiver, switch to fast mode, switch to fast mode, switch to fast mode continuously without any further information. So there is no alignment to be done. So it works perfectly robust. You can just order an evaluation board and have a look at it.
Okay. So I hope that answered the question in a proper way. Then the second question to me is progress in the development of the 3-volt transceiver specification. What are the changes in single-ended and stealth voltages? So this is not directly connected to CAN XL, but let me answer my position. So yes, there are suppliers that are looking at 3-volt implementations. However, 3-volt CAN will result in non-symmetric data communication. So that means that on the EMC side, you have a very big challenge to meet this. And we say, even if you talk about EMC, it's almost impossible to get a very stable data communication. And this is also why this single vendor that is currently introducing 3-volt CAN needs to reduce the data speed down to 1 megabit per second maximum. So NXP, we don't believe in 3-volt CAN. Simply said, you are too sensitive for external disturbances. Second one is this is solved by CAN XL. Right, so now let's connect it to CAN XL. CAN XL has this -1 to +1 volt of communication, and there you create actually this additional space, the 2-volt peak-to-peak, where you are actually very robust against all these EMC events, ground shift events, etc. So I think, also the fact that we move to a new voltage scheme within CAN XL is the main reason for this, is that we need to have more robustness in our communication signals. Does this completely answer the question? I would say not. Maybe Holger, you're also involved in the standardization around 3-volt CAN. Maybe you have an update on that one as well, just to finalize this all.
So just in the moment, we are evaluating how this can be done and what are the needed additional specifications which we need to make still a robust communication using 3,3-volt transceivers. This is mainly driven by one of your competitors, Texas Instruments, and we will see what they will achieve. There are good results in the moment that you can mix 5-volt and 3,3-volt transceivers in one network, but as you said, this is for the classic CAN and not for CAN XL.
Okay, thank you so much. Also, we have one more question from our audience. The question is for CiA. It's about the ISO specification for CAN XL was only released this year. So does CiA have any plans to promote it? How can we get people to apply CAN XL on a larger scale like they do with CAN FD or CAN Classic?
So I'm the convener of the ISO working group, which is responsible to release all these documents. And of course, we support this to as Magnus has said, we want to fix all the issues with the current specifications, and we promote them as well, of course. And if you want to see right now what is in the ISO 11898-2 not properly described, you can download free of charge from the CiA website a document where all the issues are described. Which we will fix with the ISO 11898-2 from 2025.
Okay.
Yeah. But what we can say from CiA point of view, we are promoting CAN XL because we have a lot of documents which are guidelines how to use it, and we are working on this. Sometimes they are released and other ones are under development, and here Arthur is chairman, and I think during the next year we will release a lot of documents also to support here the user of CAN XL, and also that a lot of people have here guidelines how to do the transfer from CAN FD to CAN XL.
Okay, thank you.
Yeah, maybe
Please.
Maybe it's worthwhile to add that this is not just a one-way action that CAN Automation is promoting and the others are just consuming. So we are addressing here the Chinese community, and therefore we all invite the Chinese members to come to CAN Automation, to contribute, to submit their experiences, and to join these working groups and to contribute to that work that Magnus has already mentioned.
Mm-hmm.
Okay,
yeah,
thank
sorry.
you.
Hannah, maybe I would like to suggest, because there will be a lot of different press release or different updates about the standard, then maybe we can also ask the attendees if they have interest, then they can follow up your newsletter. So could you please also send us a link in the chat? Then my colleagues will share also in the webinar room, so they can register all the newsletters, then they can get very real-time update.
So at the end of our presentation, I think we have a final slide where everything is noted. Unfortunately, we have no chat function, therefore we cannot type it there.
Okay. Okay, maybe, yeah, I think Cooper or Crystal, maybe you already have the presentation, then you can copy it out. Yeah. 那个我刚刚讲到了很多的这个技术的更新啊，技术标准啊，还有很多的应用等等。那个回头我们的助教可以发一下我们这个 CiA 官方的一个 newsletter 的一个注册信息，然后每一次他们有新的 update 的时候会发邮件过来，然后大家就可以及时收到一手消息了啊。
好的。
Okay.
So thank you. Big thanks to all the speakers and your excellent presentation and answers. So now I would like to give a closing statement to the audience, because I think it's close to our ending time. 那么好的，那么由于时间的关系呢，我们的研讨会的话就已经进入尾声了。如果还有其他问题的话，可以添加助教的微信，再进入我们的技术交流群。后续讲师的话会在技术群中为大家讲解和解答。同时我们也会在群内分享行业动态和前沿技术以及其他我们红科组织的精彩活动。如果您错过了前面的分享，也无需担心，我们也会在群中分享直播回看链接，同时整理好演讲PPT 资料，还有课程回放供大家回顾。那么至此，本次 CAN XL 线上研讨会就圆满结束。感谢大家的关注与支持，我们下次活动再见。
我们会分阶段，直播助手已经在群里面有跟大家说几个 DDL， 就是我们会分阶段，包括 PPT 视频回放，因为我们要加中文字幕，所以要下周3之前，或者是我们争取下周1。我们刚刚 update 了一个新的 deadline 是下周1之前，然后研讨会的 QA 的推文，所有刚刚问的还是说大家在直播间问的所有的问题我们会在下周5之前全部统一整理好，我们后面会有3个比较大的一个更新给到大家。
好的，感谢邱院总的补充。So all right, today's webinar has successfully concluded, and on behalf of our entire team, I would like to extend a great thank you to all our estimated international experts for sharing your valuable insights with us today. And we are grateful, very, very grateful for the time and effort you have dedicated to making it a success. Thank you, everyone. Thank you so much.
Yeah, thank you.
Thank you.
那应勤你把
我们这边就先结束一下 直播了，
Hello,
大家再见。
we-
邱院总，
All the
邱姐，
speakers wait a moment.
稍等一下哈，我结束一下直播。
哎，好的，好的，好的。
主持人怎么了？
大家下午好，欢迎来到虹科 Can XL 国际，稍等啊，欢迎来到虹科 Can XL 国际研讨会的直播现场，我是本次活动的主持人高云奇。本次活动的主办方是汽车电子与软件以及虹科。汽车电子与软件及 AAS 是一个专为汽车电子相关工程师打造的技术社区，致力于推动技术普惠以及工程师的终身学习。虹科是一家10几年的汽车电子与智能自动化技术经验的公司。我们这些年一直致力于为大家提供 CAN、KFD 等总线相关的技术方案和内容。CAN-XL 作为近年来以及未来的 CAN 网络，也将用于下一代的产品。为此，我们邀请到了国际CiA 协会的创始人 Xl and CEO Rainer Zisman， 还有博士首席技术专家 Dr. Arthur Mutter， 还有英飞凌稍等，以及英飞凌汽车网络技术首席负责人兼 CiA 技术总监 Magnus Maria Heller。恩智浦的产品营销经理 Mike Van Harder， 以及虹科智能互联技术主管陈浩6位嘉宾，为大家介绍 CAN-XL 的功能优势与传统协议网络的对比，以及目前的市场情况。再次感谢各位观众朋友的到场以及行业嘉宾们的支持。我们今天的研讨会即将开始。那么首先呢，我们先请虹科的 CEO 陈秋苑陈总为我们来一个开场的致辞，欢迎陈总。
好的，非常感谢应奇的主持和介绍，也非常感谢我们所有在线的用户朋友们，那很高兴借此机会呢，我能够代表虹科的所有同事们，在这里跟大家这个简单的欢迎词。首先呢，我想用3个关键词来开始我的这个致辞。这3个关键词分别是感谢、感激和感恩。其实虹科从2009年底开始，我们就进入了 CAN 总线的这个业务领域，到后来2012年的 CAN-FD 以及2019年我们虹科开始去接入 CAN-XL 的一些标准的制定和一些市场的反馈等等，开始做一些工作。那么其实我们在整个的过去的15年期间，虹科都有不断的参与以及不同的产品线以及不同的业务在推出，在帮助我们广大的大中华地区的用户们再去为我们的 CAN 总线的开发，为 CAN 总线的应用去赋能会去提供我们的一些支持。所以非常正式的借这个机会，感谢所有的 CAN 总线技术领域的同事们、工程师们，然后以及我们的所有的专家朋友们对虹科团队的支持和信任。我们的业务其实也从最早期的，在这15年期间，我们从最早期的 CAN 代码、CAN 的协议站、板卡分析软件不断的发展，截止到今天，我们虹科推出了非常多虹科自己的一些产品和方案，比如 CAN 总线的一致性测试系统，这个已经很多年，我们的一些hardware in loop 的 Hill 的系统、采集系统、软件服务包以及不同的软件之间打通的一些工作，以及我们的培训和测试的业务相信大家也知道，虹科在2012年开始就推出了很多 CAN 总线的一些培训业务，再到2020年我们在全网推出线上的直播课程，那么到今天为止，我们 CAN 总线相关的主题课程已经超过100节那这一路走过来，有不离不弃，不断的出谋划策，指出问题，提供非常多中肯落地、合理化、很有建设性意见的用户朋友们，也有我们过去失败不断总结，然后再成功，然后再去迭代的很多的一些宝贵的经验，才成就了今天虹科在 CAN 总线领域的一席之地。所以用3个感恩、感谢、感激、感恩来感谢我们所有的 朋友们。那之后呢，我也再讲一句，就是想用一个关键词来简单的做个总结，那么就是共创。为什么会说共创呢？其实红科一直不认为自己只是一个简单的乙方。那么从2022年开始，我们跟某个主机厂开始一起共同研发了一款系统啊。那么可能到明年我们就可以开始正式的面向市场销售啊。那之前我们是定制的一款产品，那么这个呢，在这里面我们有非常多的收获和体会，然后我们也意识到了自己确实成为这个深度参与的一份子，我们应该有一些回报。我在今年的5月中旬，我在德国的巴登参加了ICC 的CAN Conference， 这是在上一次已经14年前了啊，因为疫情推迟。那么我的很深的感受就是，整个大中华地区的的参与者只有我一位啊，然后另外还有两位来自韩国的啊，就整个亚太区的面孔只有3位。那我当时很深的感受，就这2天的闭门会议，非常多的真知灼见，非常多我觉得对于我们的用户有非常多，不管是我们是供应商，还是主机厂，还是应用者，还是开发者啊，还是系统集成商，非常多的很好的一些启发和 idea。所以当时2天会议的时候，我就马上跟其中我认为非常高价值的几位嘉宾，就今天在屏幕上大家可以看到的是几位重量级的大咖啊，我们都是 XL 的创始成员啊，然后跟他们讨论，邀请他们来举办一场针对中国的，只是针对大中华地区的我们的这个XL 的这种会议，我们一起共创，我们一起去共生，我们一起去共同成长，一起去分享全球的技术成果啊，所以我想用这个小故事来去举例说，我们希望有很多不同层面的一些共创跟大家一起去共同的，我们最重要的是一个结果，不管这个结果来自哪里，途径是什么，那我们希望在最短的时间之内，我们能够借助各种途径帮我们各方拿到更好的成果。好，所以最后有请把时间交回给应琪，感谢我们今天下午所有的大家的时间。好，
好的
Hello， 应琪。
好的，
Okay.
稍等一下，感谢陈总这边的演讲，那么大家都知道啊，稍等一下。那么大家都知道 ，CAN 技术工作呢是在 CiA 协会中完成的。作为创始人和技术先驱，我们也是非常荣幸的邀请到了 CiA 的2位 CAN 技术专家，协会创始人 Hojazet Wangje 以及 CEO René Sisman， 他们会重点介绍新一代CAN 的主要功能。那么在本次研讨会期间呢，在评论区互动的观众都可以参与线上抽奖，欢迎大家多多留言，有机会领取现金红包。相关的中文 PPT 我们也已经分享到了社群内，大家可以在评论区扫码进群，对照中文课件可以更好的理解咱们的演讲内容。第一场演讲即将开始，接下来就让我们随 CAN 创始人与 CEO 一起了解3代 CAN， 从 CAN Classic 到 CAN FD 再到 CAN XL 的整个内容。So Mr. Zelt Wangje and Mr. Sisman, please begin your speech.
Oh, sorry, Inchi. So all the speakers, maybe we can say hello now to all the audience, and then maybe we need to turn off the webcam. Okay, so 不好意思，我邀请所有的演讲嘉宾一起跟大家 say 个 hello， 然后我们待会每一个主题的时候，我们再打开 webcam 来给大家见面。好 ，Okay, so Holger, this is your turn.
Okay.
Thank you.
Okay, so welcome from the CiA side. Reinhard Sitzmann and myself, we will present the first speech, and it's titled From CAN CC, which means Classic, via CAN FD to CAN XL. But before we start with the technical topics and issues, then we will introduce ourselves. So my name is Holger Zeitranger. I'm an electronic engineer, and I was also a technical journalist for more than 40 years, and initiated the foundation of the non-profit CiA Association. Since 1992, I'm in the board of directors, and in addition, I have different roles in standardization bodies, in international ones like ISO, like IEC, SIE, and also in national ones like DIN in Germany. I hand over to Rainer. He will have the first part of the presentation, and then I will later on join you again and provide additional information.
So thank you, Holger. And thank you for the brief introduction and the honor of being part of your webinar here. And my name is Rainer Zitzmann. I hold a degree in electrical engineering too. I've joined CAN Automation in 2004. In the meantime, I am the general manager of the CAN Automation GmbH. It's the commercial arm of the association with the main objective to organize the association to provide all the services that are intended to be provided to the members of CAN Automation and to provide them in the intended and best way. Yeah, in addition to that, I'm a speaker on several conferences. We present CAN Automation on fairs and in international standardization. So not that many standardization groups as Holger does, but for example, I've standardized the communication, the CAN-based communication in light electric vehicles, public charging, or in rail vehicles, can open on the consist level. And I'm a member in further European or German mirror groups. Yeah, in brief, to CAN Automation, maybe you don't know what is CAN Automation, who is CAN Automation, why does an association like that exist? So CAN Automation, or briefly CiA, is the international users and manufacturers group that develops and supports CAN Open and other CAN-based high layer protocols. The non-profit group was founded in 1992 to provide CAN-based technical product and marketing information. The association fosters the image of CAN technology and also provides a path to future network technologies. So what does this mean? We promote CAN, we present CAN as a good alternative for everywhere where something is to be automated as embedded network. And we try to assist people in overcoming their technical challenges if they are CAN related. And so we not just network devices, but we also network humans. So we have established since 1992 a huge social network of CAN experts. And therefore, we invite also our Chinese community of CAN users to join this social network and to rely on this to benefit from this social network. So if you have any CAN related challenges, then at least you can contact CAN Automation and maybe we can help you directly, or we know someone who is very familiar with these subjects you are dealing with and can assist you so you can overcome your challenges much more easily. CAN Automation is located in Germany, in Nuremberg. So if you know Germany, for example, from the Oktoberfest in Munich, so we are about 160 kilometers in the north of Munich. And here, for example, the SBS Fair, the Embedded World Fair, some very interesting fairs for this subject to take place. So maybe you have the chance coming to Nuremberg, so you can also visit us at the CAN Automation office to discuss CAN related questions. Otherwise, we are available via email or other social media channels, so you can contact us. CAN Automation, what we are doing, we mainly maintain and develop CiA specifications with the aim to provide CAN-based devices, solutions, components, a certain degree of plug-and-play capability, of interoperability, and therefore we provide a neutral ground where companies can meet according to antitrust laws and can discuss how to overcome in a harmonized way certain CAN-related challenges. Furthermore, we provide some marketing then for these kind of specifications and these activities. So one of the famous one is the CAN newsletter magazine that appears quarterly, and it's also in China rather easily to receive as it's available as a PDF version. If you are looking for CAN-related products, tools, then maybe our product guide is a good source for information here. And if you want to know why it is reasonable to use a CAN-based solution in this or that application field, or what are benefits of this or that CAN generation, then we provide some brochures on our website where you can get the information. On the other hand, we have also some technical-oriented services, educational services like trainings also for engineers in China. We offer the possibility via web-based seminars or on-site seminars to train your staff. And furthermore, we offer testing services for CAN Open. We have conformance assessment. On the other hand, for certain application fields, we organize together with our members interoperability tests, or more easily to speak, simple plug fests, where you can double check whether your implementations are interoperable with implementations of competitors, of other actors active in the market. Yeah, so much in brief with regard to CAN and automation. Once again, warm welcome to this event from our side. So briefly to our topic. So from CAN Classic to via CAN FD to CAN XL. So in the late 70s, early 80s, the complexity in automotive in-vehicle networking increased that way that it was via direct wiring concepts very difficult to extend the existing automotive wiring harnesses via further functionality. The cabling had a lot of weight, and therefore the car makers came to the conclusion that it's not very future-proof, the current way networking goes on in the cars. And therefore they came to Bosch and said, could you assist us, could you help us in developing something to simplify automotive in-vehicle networking? And the development was presented then in 1986. So you see here the first press release from these days. And there Bosch presented the controller area network, or briefly what you call now today CAN, or more specific today CAN Classic, or abbreviated with CAN CC. So from these days on, CAN Classic made its way into the cars, but it was not limited to the use in automotive applications. So very soon in the 90s, the CAN migrated to truck applications, heavy duty vehicles. In the meantime, we find CAN in building automation, access door control, elevator control. We find CAN-based solutions in medical application fields like X-ray stands, communication to contrast media injectors, patient beds, and acute care units. Furthermore, we find the CAN in energy management applications, energy generation, so solar power plants, windmills. So in almost every area where something is to be automated, we find CAN-based networks in the embedded area. And we can say sometimes CAN is the dominating network, like in commercial vehicles, construction vehicles, heavy duty vehicles, and sometimes CAN is just available in a niche market, but in general, we find it anywhere where something is to be automated. So from this side, the situation looks very promising with regard to CAN-based technology. Nevertheless, we see over the years more and more requirements have been placed on embedded networking. And therefore, we have also to think about how can we meet today's and also future's requirements to embedded networking, also in CAN-based communication. And the first step came then in 2012, when Bosch presented on occasion of a CAN Automation's International CAN Conference, the CAN with flexible data rate, so to say, the second generation of CAN, which provides a higher data throughput in CAN-based networks. And further requirements came up, and also those have to be met, maybe a little bit earlier than we would have expected that, but already end of 2018, beginning of 2019, the development of CAN XL, CAN with extended data field, started and was then finalized in 2021. And it's meanwhile internationally standardized. So you see on this slide the history of the documentation, respectively the specification and standard of standardization of CAN, which started with a presentation at the SAE conference in 1986. Then you have the Bosch specification available in 1991. It's rather famous, the CAN 2.0 AB, because it's also today still mentioned in some CAN controller data sheets to indicate that in this communication media, which is based on message addressing, you have a very interesting attribute, the so-called CAN identifier, that identifies in CAN Classic the priority as well as the data content. Exists in two formats, the 11-bit and the 29-bit identifier, and typically in CAN controller data sheets, this indicates that they are capable to run both addressing formats. Yeah, this specification was then submitted to ISO, and in 1993 there appeared the first CAN standard, ISO 11898, which covered that what we call today CAN Classic, the protocol, and the high-speed transceiver. So in 2003, this document had been revised and was split in two parts. A first part that is dealing with the data link layer and the physical coding sublayer, and the second part that covers the high-speed physical medium attachment, so what we call more or less the transceiver. We have there also the test plans, so the automotive industry wants to use tested components, so therefore we have standardized test plans in the document 16845. Around this standard series was extended by further functionality, but for the moment we just focus that when CAN-FD came up, there was the discussion where to standardize CAN-FD now, and after some discussions the result was why not merging CAN-FD and CAN-CC to the same international standard. And so since 2015 and 16 we have now our ISO 11898-1 and 2 specification standard series covering CAN-CC and CAN-FD, and we updated the test plans. And finally, since 2024, so since spring of this year, we have now the ISO 11898-1 and 2, the part 1 covers the CAN Classic, CAN-FD, and CAN XL data link layer. And the part 2 introduces some new terms, but in general it covers still the high-speed physical medium attachment, but also a physical layer more suitable for CAN-FD, the CAN-SIC, as well as the SIC CAN XL physical medium attachment sublayer implementation. So this means I have a certain flexibility. Holger will tell us about this later on, to optimize the communication also on the physical layer level to end up in a real, let's say, super speed mode in CAN-based communication. So why was all this necessary? So we see here a little bit the development of in-vehicle networks. So we see here some legacy networks which were installed at the beginning of this millennium. And we see here, okay, we had a CAN network for dedicated tasks, so for comfort, body electronics, so for controlling the drivetrain, the motor management, and automotive networking is typically a subject that is very cost sensitive. So therefore, the car makers evaluate also at the lower end, can we save costs on a certain to a certain extent, maybe at the lower end. Therefore, sometimes CAN is complemented by LIN, the local interconnect network, or there are some other tasks where you need a little bit more performance, maybe for multimedia applications. CAN, as the name said, is a controller area network designed for starting, stopping applications, communicating in a robust and reliable way a certain analog value. But CAN has never ever been designed for data streaming. So therefore, maybe other communication techniques for multimedia applications have been used. But the complexity in automotive networking increased. So therefore, And the next step was to shift to a so-called domain-oriented in-vehicle network architecture. So you have not just a single CAN network for the body control, for the control of the chassis electronic and so on, but you have entire heterogeneous networks. And all of these domains are controlled by a so-called domain controller, and they have to synchronize somehow their process images via very fast communication links via automotive Ethernet. So you see very complex architectures. And in this design, you have a disadvantage that you have to place cross wires across the car. So maybe to network all the electronic control units for the braking or for other applications. And therefore, there was also some idea to future network architectures we will have soon. And furthermore, you can see, or you can simply assess that approaches like that are very communication demanding. So we had here an insight from Mercedes, which showed us via several generations of CAN networking in the Mercedes E-Class, how straightforward the amount of ECUs was increased and how the amount of messages needed to communicate in such a car more or less exploded. So therefore, it was very soon clear, okay, we have to increase the data throughput in CAN-based networks or in automotive networking in general. And one step in this direction was the CAN with flexible data rate, so to allow a higher data throughput. And the development took place in a way that the major attributes of classic CAN Classic should be kept. So as the design simplicity to have a high reliability and robustness, and on the other hand, the data throughput should be extended. Unfortunately, one major attribute that reduces the configuration effort to a minimum, the priority management of the CAN messages in the CAN identifier demands and so-called in-bit time response, which is also, unfortunately, a limiting factor in the speed and brings the CAN Classic to those speeds that you may know today if you are a CAN Classic user. But as soon as it is negotiated who is the sender, you don't have anymore a so-called in-bit time response that tells you, hey, there's another outside who has a high prior message. Then it is clear who is the sender, and you enter up a certain streaming phase. In this streaming phase, you can turn up the speed to what your physical layer is capable to drive. And after you have transmitted more or less your data, then you have at the end of a CAN communication the acknowledgement to be sure that at least someone has received your data correctly. And in this acknowledgement, once again, we have an in-bit time response. And therefore, we have the same restrictions as at the beginning of the CAN frame. And this means in between, we can transmit with a higher data rate, and we can increase the amount of accelerated transmitted bits as we lengthen the data field. So Holger will show this in a CAN frame comparison. So for the moment, we just see, okay, we can accelerate in CAN with flexible data rate for the transmission of the data. So we had now with CAN-FD the possibility to transmit a higher data throughput, but as I've said, domain-oriented architectures have the disadvantage that you need a high cabling effort, and to reduce this cabling effort, there's a next transition in in-vehicle network design. It's the so-called zonal architecture. You have just zone controllers, and they integrate via some cabling all electronic control units that are occasionally next to them, and then they collect all the data and update the process image with the other zone controllers that on a higher level you can run the entire application. And this means also some requirements to the data. The data has to be somehow self-descriptive. You have to know from which area, from which sensor, from which electronic control unit is this data derived, under which condition was it measured or generated, to which kind of application does this data belong. So all these things that you also know from cloud computing are now also applicable in this zonal architecture. So you put a lot of more requirements on the way you communicate in the embedded networks. So this is more or less the driver for the development of CAN XL. Prior to come to this CAN XL, I like to mention that also some improvements at the lower end in CAN-FD communication were introduced. If you have to integrate, for example, a lot of simple devices, let's say, you can also have a cost-sensitive solution. It's the CAN-FD Lite communication that had been invented. So CAN-FD Lite is intended for use in deeply embedded, price-sensitive sensor actor networks. So the necessity for a lightweight CAN-FD network became evident during the development of systems for modern car lights. The connected LED clusters are controlled individually by one commander node. The communication follows a commander-responder schema. And the responder nodes do not support network arbitration. They only transmit CAN-FD data frames on request of the CAN-FD Lite commander. So accurate clock source at each node is not required. So this means there's a lower cost and improves the implementation reliability. Yeah, so nevertheless, we think about high data throughputs also. So therefore, we have some additional requirements derived from the SUL architecture. So we want to have scalable networks regarding bitrate, data length, data throughput. We want to integrate legacy approaches. We need to think about, therefore, on multiple higher.
Very, very grateful for.大家下午好，欢迎。